Hello there, and welcome to the Cosmographer. In a single second, one galaxy on this list releases as much energy as our Sun will emit in 10,000 years, and almost none of that light ever reaches a human eye. That is only number 6. Also waiting tonight is a spiral so wide you could lay 6 Milky Ways across its face, which hid from every telescope on Earth until 1986 because it barely glows. There is a galaxy that astronomers weighed and found missing most of what the universe is supposed to be made of. There is a galaxy that was discovered because the largest steerable telescope on Earth was pointed at the wrong coordinates, and the empty sky answered, from a place where no star has ever formed. And the galaxy at the top of this list holds the most absolute record in astronomy, an object so far away that nothing we ever build, send, or say can reach it, and we will save it for the very end. 10 galaxies, counted down from 10 to 1, each one breaking a rule the universe was supposed to enforce, and every one of them forever beyond our reach. Get comfortable and settle in. If falling asleep somewhere out among the galaxies sounds like a good night to you, a quiet like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the word never will mean something new. Let's begin at number 10. Number 10, Malin 1, the invisible giant. There are 10 galaxies on this list, and not one of them will ever be visited by anything human. That is not pessimism. It is arithmetic. The nearest object we will meet tonight sits about 72 million light-years away, which means a spacecraft moving at the speed of our fastest probes would need more than 1 trillion years to arrive. The farthest object on this list is stranger still. It sits, at this moment, roughly 33.8 billion light-years from Earth, and the space between us and it is stretching faster than light itself can cross. Nothing we send will ever arrive there. Nothing we say will ever be heard there. These are places we can know but never touch, and that is precisely what makes them worth 3 slow hours of our attention. Before we begin the descent, it helps to write out a short inventory. A galaxy, we are taught, is a simple kind of thing. It shines because it turns gas into stars. It spins, and its arms trail behind its rotation like hair behind a runner. It holds a deep reservoir of dark matter, the invisible scaffolding that gathers everything else. It keeps a great black hole at its center, the way a city keeps a courthouse. And it takes its time growing up, assembling slowly across billions of years. 5 rules, learned from 100 billion examples. Tonight we will meet 10 galaxies that, between them, cross out every line on that list. We will rank them by the depth of the mystery, by how badly each one breaks the rulebook, and as we climb toward number 1, the distances will grow until distance itself becomes the final mystery. Get comfortable. We have a long way down to go, and the first entry is a giant that spent the whole of human astronomy hiding in plain sight. Number 10 on this list is Malin 1, the invisible giant, and it earns its place with a simple, uncomfortable fact. It is one of the largest spiral galaxies ever found, and nobody saw it until 1986. It sits about 1.19 billion light-years away, in the constellation Coma Berenices, near the North Pole of our own galaxy's sky. Its disk spans roughly 650,000 light-years. Our Milky Way, for comparison, spans about 100,000. You could lay 6 galaxies like ours across the face of Malin 1 and still have room left over at the edges. If Malin 1 sat where the Andromeda Galaxy sits, it would sprawl across a stretch of our night sky, dozens of full moons wide, a structure so large it would dominate every autumn evening. And yet, if it sat there, you still might never notice it. Because Malin 1 barely glows. Astronomers measure the brightness of a galaxy's surface the way a mapmaker measures the density of a forest, patch by patch of sky. Malin 1's surface shines at roughly 26 magnitudes per square arcsecond in visible light, and that number, once translated, is remarkable. It means the galaxy is dimmer than the faint chemical glow of Earth's own upper atmosphere at night. The air above your head, on the darkest night of your life, outshines this galaxy. It belongs to a class called giant low-surface brightness galaxies, objects whose light is spread so thin that the night sky itself becomes a curtain in front of them. Every photographic survey of the 20th century looked straight through it. The largest spiral disk in the local universe was not hiding behind anything. It was simply too quiet to register. The discovery, fittingly, was less an observation than a darkroom accident. David Malin was an astrophotographer at the Anglo-Australian Observatory, and he had invented a technique called photographic amplification, a way of coaxing faint, buried light out of long-exposure survey plates. The method was chemistry as much as astronomy, a careful redevelopment of the plate that lifted whispers of signal above the fog. Working with the astronomers Gregory Bothan and Chris Impey, Malin applied his technique to plates of the Virgo region, hunting for small, faint dwarf galaxies. On one plate, something emerged that was not a dwarf. It was a wide, pale smudge with a bright center, and when the team took its spectrum in 1986, the answer rearranged the problem entirely. The smudge was not a small thing nearby. It was an enormous thing far away, a spiral disk of almost absurd size, sitting more than 1 billion light-years out. The plates had held it for decades. The sky had held it forever. It took a photographer's darkroom trick to make the universe hand it over, and the object was named, by the plain habit of cataloguing, after the first entry on David Malin's list. The photographer got the galaxy. Arguably, the grandest spiral known carries the name of the man who developed its picture. The mystery of Malin 1 is not its size. It is its silence. This galaxy is one of the most gas-rich objects known, holding tens of billions of solar masses of neutral hydrogen, several times the raw star-making fuel of the Milky Way. By some estimates, the reservoir reaches 50 billion solar masses of hydrogen, among the largest supplies of any spiral ever measured. And here is the rule that reservoir is supposed to obey. Gas that gathers becomes clouds, clouds that gather collapse, and collapse ignites stars. A galaxy with that much hydrogen should blaze. Malin 1 never did. Its gas lies spread so thin across that enormous disk that it sits below the critical density where clouds can condense, and so star formation proceeds at a trickle, a few sparks scattered across 500,000 light-years of twilight. It is a bonfire's worth of fuel spread one twig at a time across a continent. Nothing is missing. Nothing is broken. The galaxy simply never turned itself on, and after nearly 4 decades of study, nobody can say with confidence why. For 30 years, even its shape was misread. Early observers classed Malin 1 as a modest galaxy wrapped in a huge, formless envelope of faint light. Then, in 2007, a careful analysis of archival Hubble imaging found something tidier and stranger. The center of Malin 1 is itself a complete, ordinary barred spiral galaxy, about 30,000 light-years across, with a bulge and a bar and everything a respectable galaxy should carry. A normal galaxy sits embedded like a seed at the heart of the vast dim disk, and if the outer disk did not exist, that inner spiral would attract no attention at all. Then, in 2016, deep imaging with the Canada-France-Hawaii telescope on the summit of Mauna Kea resolved the outer disk itself, and the formless envelope resolved into structure. There are spiral arms out there, enormous ones, with single-arm segments up to 33,000 light-years across. One segment of one arm of Malin 1 is wider than most complete galaxies. The invisible giant is not a cloud. It is a true spiral, drawn at a scale and a faintness that the universe apparently permits but almost never chooses. How does such a thing come to exist? The honest answer is that no one knows, though there are suspects. A small companion galaxy, catalogued as Malin 1b, sits about 46,000 light-years from the center, close enough that its gravity may have stirred the inner regions and helped shape the inner spiral. A second, more distant neighbor has been proposed as a partner in an ancient close pass, an encounter that might have drawn the giant disk outward like pulled taffy, spreading gas across those hundreds of thousands of light-years without ever compressing it into stars. Computer models can be persuaded to build a Malin 1 this way, slowly, gently, without violence. But models can be persuaded of many things. What the observations actually show is a galaxy with a dozen open questions, orbiting a simple central fact. The universe built its largest known spiral in near total darkness and then let it run. The companion itself deserves a sentence of respect. Malin 1b is a small, faint galaxy, the kind that would be forgettable anywhere else, and its projected distance from the giant's center is shorter than the radius of the giant's own disk. In other words, the companion orbits inside the footprint of the galaxy it accompanies, a moth circling within the span of the cathedral. Encounters between such mismatched partners rarely destroy anything, but they stir. A gravitational wake from Malin 1b could have rippled inward and helped organize the inner bar and spiral, while leaving the outer ocean of gas undisturbed and unlit. If that is what happened, then the one bright, finished part of this galaxy owes its existence to a passing gnat, while the giant itself stayed asleep through the visit. Consider what the timescales out there mean. The outer disk turns so slowly, and its circumference is so long, that a single orbit at the rim takes on the order of 1 billion years. Since the universe began, the edge of Malin 1 has completed perhaps a dozen circuits. A star out there could carry a planet through one full galactic year, while trilobites rose and vanished on Earth, and through another, while the dinosaurs did the same. The light now arriving from Malin 1 left it about 1.19 billion years ago, before the Cambrian explosion scattered complex life through Earth's oceans. We are seeing the giant as it was when our world belonged to microbes. And this is where the distance stops being a number and becomes a wall. 1.19 billion light-years means that even light, the fastest thing permitted, spends over 1 billion years on the crossing. Any probe we could build would take thousands of times longer. For a journey like this one, the speed of light is not fast enough. Hold on to that sentence. It sounds like a complaint about engineering. By the end of this list, it will become a law of nature. Picture the inside of that disk for a moment, because it may be the strangest quiet place in the nearby universe. You are floating somewhere in Malin 1's outer arms, 500,000 light-years from its heart. By every definition, you are inside a galaxy, inside one of its spiral arms, in what should be a boulevard of crowded starlight. But the sky around you is mostly darkness. The stars here are spread so thin that the nearest one is a distant lantern, and the next is farther still. There is no glowing band across the heavens, no city of light, only a faint, pale rumor low in one direction, which is the galaxy's own center, 30,000 generations of light travel away. Cold hydrogen drifts past you in quantities that could build constellations, and it builds nothing. It has drifted like this since before Earth existed. If you waited here a human lifetime, nothing would change. If you waited here 1,000,000 lifetimes, the sky would rearrange itself only slightly, the way a glacier rearranges a valley. You are standing in the middle of the largest cathedral ever raised, and the lights were never switched on, and you cannot even tell you are indoors. There is one more reason Malin 1 matters, beyond its own strangeness. Its discovery raised an unsettling question about the census of the universe. If the grandest spiral known could hide below the airglow of our own atmosphere until 1986, what else is hiding there? Low surface brightness galaxies may account for a large fraction of all galaxies by number, a hidden population crouching beneath the detection thresholds of our surveys. Some astronomers called it the crouching giant problem. Every census of galaxies we conduct is a census of the willing, the objects bright enough to answer the knock. Malin 1 is proof that the quiet ones exist and that they can be enormous. Some estimates suggest that galaxies below the classical brightness thresholds could rival the bright population in sheer numbers, which would mean our maps of the universe have been drawn from perhaps half the inhabitants, the talkative half. The stakes are not small. Counts of galaxies feed into measurements of how much ordinary matter the universe holds and how structure grew across cosmic time, and a hidden population bends those numbers. Modern instruments have taken the hint. The same appetite for faint, wide structure that Malin 1 exposed helped motivate a new generation of telescopes and surveys designed specifically for low surface brightness light, cameras built to notice whispers. Later surveys did find other giant low surface brightness disks, cousins of the first, but after nearly 40 years, Malin 1 remains the defining specimen of its class, the one that taught astronomy how much can be missed. David Malin's darkroom technique, it is worth adding, also revealed vast faint shells of stars wrapped around elliptical galaxies, another whole category of structure that had been sitting unseen in old photographs. The lesson repeats. What we can see has never been the same as what is there. It is worth pausing on how astronomers even weigh a thing like this, because the weighing is its own quiet feat. The starlight of Malin 1 is too faint to inventory directly across most of its disk, so the census of its fuel comes from radio astronomy. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Point such a dish at Malin 1 and the hum is loud, astonishingly loud for a galaxy so dim, and the breadth of the signal reveals the rotation of the disk that carries it. The gas at the far side of the galaxy is swinging away from us, while the near side swings toward us, and the spread between those motions measures the gravity holding the whole structure together. The disk is real, the rotation is orderly, and the mass is enormous. Radio astronomers sometimes note that if our eyes saw in the 21-centimeter line rather than in visible light, Malin 1 would have been famous a century ago, a monster stretched across the sky. Our biology chose the wrong wavelength, and so the giant needed a darkroom to introduce itself. The inner galaxy deepens the puzzle rather than easing it. That central barred spiral, 30,000 light-years across, appears to be a perfectly conventional object, with normal colors, a normal bulge, and stars of respectable age. It seems to have lived a normal life on a normal schedule. That means Malin 1 is not simply a failed galaxy, an object that never managed to begin. Something in its history built an ordinary spiral first, and then wrapped it in 500,000 light-years of dim, slow-turning disk, either gradually, gas settling from far out over billions of years, or in one ancient gravitational accident that has long since tidied up its own evidence. Each version leaves fingerprints that astronomers have looked for, warps and streams and asymmetries, and the observations so far refuse to settle the case. A galaxy inside a galaxy, the small one bright and finished, the vast one dark and barely begun, both sharing one center. There is nothing else quite like it within a billion light-years of home. So the first rule falls. A galaxy is supposed to shine, and here is one, 6 times the width of our own, that spent 13 billion years declining to. It holds the fuel. It holds the architecture. It holds spiral arms wider than whole galaxies, turning once a billion years in the dark. And it sits at a distance that makes the question of visiting it not difficult but meaningless, a place we could aim at forever and never approach. Malin 1 keeps its own counsel at the bottom of this list, the gentlest of the 10 mysteries, a giant that simply never raised its voice. But at least Malin 1 has a familiar shape, a spiral we can recognize even in the dark. The next galaxy on this list looks like nothing else in the sky, as if someone had drawn a bright, perfect target around an empty center and then declined for 75 years to explain the drawing. Number 9. Hoag's object, the perfect ring. Number 9 on this list is Hoag's object, and the simplest way to introduce it is to admit that it looks designed. Every survey of galaxies contains its share of odd shapes, wrecks and smears and tangles, the ordinary vandalism of gravity. Hoag's object is not one of them. It is a near-perfect circle of blue young stars, about 121,000 light-years across, slightly wider than the entire Milky Way, wrapped around a compact yellow core of old stars, about 24,000 light-years across. Between the ring and the core lies a gap that appears, in every photograph ever taken, to be almost entirely empty. It sits roughly 600 million light-years away, in the constellation Serpens, and when the Hubble Space Telescope photographed it, the result looked less like a galaxy than like a diagram of one, a textbook figure drawn with a compass. The ring is so round and the core so neatly centered that the eye refuses to accept it as an accident. And for 75 years, astronomy has been unable to explain how it was made. The story begins in 1950 with a young astronomer named Arthur Hoag scanning photographic survey plates. Among the thousands of smudges, he noticed a tiny ring with a bright center, and he published a short, honest note flagging it as a peculiar object. His confusion was reasonable. The thing resembled a planetary nebula, the luminous shell that a dying sun-like star puffs into space, but it was far too large and far too distant for that. So Hoag offered another possibility, and it was an elegant one. Perhaps the ring was an illusion. Perhaps the core's gravity was acting as a lens, bending the light of a more distant object behind it into a circle, the phenomenon Einstein's relativity predicts, and astronomers now call an Einstein ring. In 1950, gravitational lensing had never been observed. Hoag was proposing, in a one-paragraph note, that his little smudge might be the first example in history. It was a beautiful guess, and it was wrong. Later spectroscopy delivered 2 decisive facts. The core and the ring share the same redshift, meaning they sit at the same distance and belong to a single object, not a chance alignment of 2. And the core is nowhere near massive enough to bend light into a ring of that size. Gravitational lensing was eventually discovered elsewhere, in 1979, with far heavier lenses. Hoag's ring is not a mirage. It is a real structure, 121,000 light-years of newly minted blue stars arranged in a circle, orbiting a core that offers no explanation for them. Rule out the illusion, and you are left holding the object itself, which is harder. Astronomy does have a standard machine for making rings, and it is worth describing, because its failure here is the heart of the mystery. The famous ring galaxies, like the cartwheel in the constellation Sculptor, are made by collision. A small galaxy plunges straight through the heart of a larger spiral, like a stone dropped through a pond, and the gravitational splash races outward as a ring-shaped wave, sweeping up gas and igniting stars as it goes. The recipe leaves evidence everywhere. Bullseye rings are ragged and lopsided. The struck galaxy is disturbed, its core often knocked off center. And the culprit, the small intruder, is caught nearby, fleeing the scene at high speed. Astronomers have photographed dozens of these accidents, and they all look like accidents. Hoag's object looks like the opposite of an accident. The ring is crisp and circular. The core is serene, round, and undisturbed, with no sign it was ever punched through. And there is no culprit. Deep images of the surrounding sky show no disturbed neighbor, no debris field, no tidal wreckage, nothing plausible fleeing. If a collision built this ring, it happened at least 2 or 3 billion years ago, long enough for the intruder to escape beyond recognition and for every scar to heal. Yet the ring's stars are young and blue, which means the ring is still forming stars right now. A billion-year-old wound does not keep bleeding fresh light. Something is sustaining this circle in the present tense. So the theorists went looking for gentler machines. One idea holds that the core once had a bar, the straight spine of stars that crosses the middle of many spiral galaxies, our own included. Bars are efficient movers of material. A strong bar can fling gas outward and park it in a ring, and bars can, under some conditions, dissolve after a few billion years, leaving the ring as an orphan. The astronomer Noah Brosh proposed a version of this story in the 1980s, and it has one large problem. The core of Hoag's object appears perfectly round, with no trace of a bar, and the dynamics of round, pressure-supported cores make them poor hosts for the strong bar the story requires. The suspected sculptor not only left the scene, it may never have been able to hold the chisel. The other family of explanations is quieter still. Perhaps the ring was never flung outward at all. Perhaps it fell inward or drifted in from beyond. In this picture, sometime billions of years ago, the core, an old, round, finished galaxy, encountered a supply of cold gas. It may have shredded a passing gas-rich dwarf galaxy and inherited its material. It may have sipped from a cold filament of the intergalactic medium, the vast threads of hydrogen that lace the space between galaxies. However it arrived, the gas settled, as orbiting gas does, into a circular lane, and there it condensed into stars, lighting up a ring around a core it never touched. Astronomers call this accretion, and it has a real virtue. It explains the calm. No collision, no scars, no fleeing culprit, just a slow delivery and a slow ignition. Radio observations add support, showing that the visible ring rides on a much larger disk of neutral hydrogen, a reservoir of raw fuel wrapped around the whole system, quietly feeding the circle of new stars. But accretion has its own embarrassment. Nobody has caught the machinery at work. The gas is there, and the ring is there, and the chain of events connecting them is a story we tell because it is the least impossible one available. A theory that explains everything except how it started is not yet an answer. It is worth lingering on the cartwheel comparison because the contrast teaches by failure. The Cartwheel galaxy sits about 500 million light-years away, a distance comparable to Hoag's object, and it too wears a ring of young blue stars roughly 150,000 light-years across. But everything else about it confesses. The Cartwheel's ring is visibly expanding, racing outward from the ancient point of impact, and inside it, the galaxy's old spiral structure hangs in tatters, spokes of disturbed material connecting the wreckage to the rim, which is what gave the galaxy its name. Off to one side sit two smaller companion galaxies, and one of them is widely suspected of being the Bullet. Astronomers can run the collision backward on a computer, watch the intruder punch through, and reproduce the ring's size and speed within reasonable bounds. The case practically closes itself. Now set the two portraits side by side. Same distance, same blue ring, same scale, and one of them is a solved crime scene, while the other is a sealed room. Hoag's ring is not expanding in any measurable hurry. Its interior holds no spokes, no tatters, no ghost of a former spiral, only that smooth, dignified core. The comparison is the mystery in miniature. When the universe builds a ring by violence, it cannot help leaving fingerprints, and this ring has none. There is also the question of what keeps a circle circular, which is less obvious than it sounds. A galaxy's disk does not rotate as a solid object. Material closer to the center completes its orbit in less time than material farther out, and over hundreds of millions of years, that difference smears almost any pattern into a spiral or a blur. A narrow ring should suffer the same fate unless its material shares very nearly the same orbit, a single circular lane with little spread in radius. That is exactly what the gas in Hoag's ring appears to do, moving along its circle at a couple of 100 kilometers per second, orderly as a planet. Whatever delivered this gas did not merely deliver it. It delivered it onto one narrow, nearly perfect orbit and left almost nothing anywhere else, which is either a remarkable coincidence or the signature of a slow, resonant process astronomers have not yet reconstructed. Some models appeal to orbital resonances, the same clockwork that carves gaps in Saturn's rings and shepherds their edges, operating here at a scale 100,000 light-years wide. The mathematics is willing. The history remains missing. And the gap, it turns out, may not be perfectly empty after all. Careful processing of deep images suggests traces of a faint, diffuse disk of stars spanning the space between core and ring, far too dim to see in the standard portraits. If that faint disk is real, it whispers an important hint because it means the region was not always vacant, and the system may once have been a more continuous structure whose middle zone faded or emptied while its inner and outer parts endured. Follow-up observations have chased that whisper without settling it. Even the emptiness of Hoag's object, in other words, is provisional, and the sharpest images we possess still leave room for an entire hidden disk of stars between the circle and its center. An object this well photographed should not have secrets left at this size. It does. Meanwhile, the object itself keeps adding small flourishes, as if aware of its audience. In the dark gap between the core and the ring, Hubble's famous image happens to capture a second ring galaxy, far more distant, shining through the opening like a signature inside a signature. It is pure coincidence, a chance alignment through the one clear window the foreground object provides, and it is the kind of coincidence that makes astronomers smile and look twice at their screens. The brightness of Hoag's object hovers around 16th magnitude, which places it within reach of large amateur telescopes as a faint, round smudge. Thousands of stargazers have found it from dark backyards, knowing that the smudge in the eyepiece is the most perfect circle the universe is known to have drawn, and that nobody can say why it is there. The numbers behind the image deserve a moment, because the scale is easy to lose. The ring's stars are hot, massive and blue, the kind that burn their fuel in mere millions of years and detonate. A structure whose glow depends on such stars cannot coast. It must be replenished continuously, generation after generation, which means the ring has been an active stellar nursery for a very long time, cycling through short-lived giants while maintaining its shape. And the shape is the deepest part of the trick. Ring, gap, and core have remained in a stable orbital arrangement for billions of years. Whatever built this structure did not build a firework. It built an architecture, a configuration of star and gas orbits balanced well enough to persist for a meaningful fraction of the age of the universe. Galaxies of this type, with a detached luminous ring around a round core and no bar, are catalogued as Hoag-type galaxies, and they are vanishingly rare, on the order of 1 in 1,000 galaxies, with Hoag's object itself the cleanest example known. Too rare to study as a population, too real to dismiss as a fluke. Rarity, in astronomy, is its own kind of clue, and nobody has read this one successfully. How do astronomers know the ages they keep citing here? The method is color, used with care. Stars are born in a range of masses, and the massive ones are blue, furious, and brief, while the small ones are red, patient, and nearly immortal. A population of stars therefore changes color as it ages, like an ember, blue-white in its first few million years, then whitening, then yellowing as the giants die off and the modest stars inherit the sky. Point a spectrograph at the core of Hoag's object, and the light reads old, a settled yellow population with billions of years behind it. Point it at the ring, and the light reads young and keeps reading young, with the ultraviolet signature of stars that cannot be more than a few million years old, over and over along the circle. 2 clocks, 1 object, telling different times. The core finished its story long ago. The ring is mid-sentence. Any explanation must hold both clocks in one hand, and that requirement alone has eliminated most of the easy answers. Arthur Hoag himself went on to a distinguished, useful career, eventually leading the stellar division at Kitt Peak National Observatory, measuring stars, running telescopes, doing the steady work of the field. His 1950 note, a single paragraph of honest puzzlement written at the start of it all, became the most famous thing he ever wrote. There is something quietly instructive in that. He did not solve the object. He did not even claim to. He noticed it, described it plainly, offered his best 2 guesses, and both guesses eventually failed, and the noticing still turned out to be the lasting contribution. Science keeps a special shelf for well-described mysteries, and Hoag's shelf has now outlived Hoag, and his object still declines to explain itself to anyone. Imagine, briefly, the view from a world inside that ring. Your sun is one of the young blue giants, or more likely one of the smaller, longer-lived stars born alongside them, and your night sky is unlike any other on this list. Ahead of you and behind you, along the ring, the sky burns with a dense band of brilliant young stars, a luminous avenue curving away in both directions until perspective closes it. Look inward, though, across the gap, and there is a strange, formal emptiness, a dark moat, tens of thousands of light-years wide, and beyond it, a great, soft, golden glow, the old core, hanging in your sky like a lamp behind frosted glass. The core's stars are billions of years older than everything in your neighborhood. From your avenue of young light, you look across the moat at an ancient city you can never visit, and its light is old, and yours is new, and nothing in your sky explains why the 2 of you are arranged in this perfect geometry. Astronomers on that world, if there are any, presumably have their own name for the puzzle, and are no closer to solving it than we are. And of course, there is no going there to check. 600 million light-years is a figure that quietly ends every fantasy of inspection. The light we receive tonight from that ring left it when the first complex animals were assembling themselves in Earth's oceans. Any reply we could send, any probe, any signal, would spend 600 million more years in transit, arriving, if anything can be said to arrive, at an object that will have orbited itself into some unknowable future arrangement. We will only ever know Hoag's object as an image, a finished portrait delivered at the speed of light, with the working hidden. A ring with no maker is strange, and it may stay strange forever. But the next galaxy on this list breaks something more basic than shape. It breaks direction, the simple question of which way a galaxy is allowed to turn, and it took 2 astronomers most of a decade and the Hubble Space Telescope to prove that it was breaking it. Number 8. NGC 4622, the galaxy that spins the wrong way. Number 8 on this list is NGC 4622, and its mystery is invisible in any single photograph. It sits in the southern constellation Centaurus, at a distance that published measurements place somewhere between about 100 and 200 million light-years, and in images it looks conventional to the point of boredom. A bright, smooth core. Graceful, well-drawn arms. A tidy disk, seen almost perfectly face-on, like a dinner plate viewed from directly above. Nothing about the picture warns you. The strangeness of NGC 4622 is not a matter of shape or color or size. It is a matter of direction. This galaxy's outer spiral arms point the wrong way. To feel why that sentence matters, you need one piece of galactic mechanics, and it is a piece worth owning, because it governs every spiral you will ever see. The galaxy's disk does not rotate like a solid wheel. It rotates like coffee stirred in a cup, with the inner material completing its circles far faster than the outer material. Astronomers call this differential rotation, and its consequence is relentless. Any pattern painted onto such a disk gets sheared, dragged, and wound up by the difference in speeds, and the winding always goes one way. Over hundreds of millions of years, arms are combed backward so that they trail the rotation, curling away from the direction of spin, the way a runner's hair streams out behind her, the way water spirals as it drains. Trailing arms are not a preference. They are what shear does to structure, everywhere, automatically. Survey the sky, and you find spiral after spiral obeying, thousands upon thousands of them, so reliably that for decades astronomers used the arms as a shortcut. Look at which way the arms wind, and you know which way the disk turns. It was one of the field's small, dependable certainties, the kind of rule nobody bothers to state because nothing has ever broken it. NGC 4622 broke it. The galaxy has 2 prominent outer arms winding in one direction, and, tucked closer to the core, a single fainter inner arm winding in the opposite direction. Stop and picture that. Whatever way this disk rotates, some part of the pattern is winding against it. If the outer pair trails, the inner arm leads, opening into the rotation like a fan blade reversed against the wind. If the inner arm trails, then both strong outer arms lead, which is worse. There is no way to spin this galaxy that makes all of its arms behave. The object is a contradiction wearing the costume of an ordinary spiral, and the costume worked for most of a century, because with the disk face on, its rotation is almost entirely sideways to our line of sight, and nothing in an ordinary image reveals which way it turns. 2 astronomers at the University of Alabama, Gene Bird and Ronald Buter, decided to interrogate it properly, and the interrogation took the better part of a decade. Their problem divided into 2 questions, each hard in its own way. First, which way is the disk actually rotating along our line of sight? That part yields to spectroscopy. Gas on one side of a rotating disk swings toward us and its light shifts slightly blue, while gas on the far side swings away and shifts slightly red. Read the shifts across the disk, and you have the rotation, at least as a left-right answer on the sky. Second, and much subtler, which edge of the tilted disk is nearer to Earth? The galaxy is not perfectly face-on. It is tipped by a whisper, and that whisper decides everything, because the same observed rotation means opposite things depending on whether the near edge is the top or the bottom of the image. Get the near side wrong, and every conclusion flips. The two questions together form a geometry problem stretched across 100 million light-years, and the second question cannot be answered by spectra at all. It has to be answered by dust. In May of 2001, Bird and Buter aimed the Hubble Space Telescope's Wide Field and Planetary Camera 2 at the galaxy, and the resulting image was sharp enough to read the disk's fine grain. Dust settles into a galaxy's disk plane, and when you view a slightly tilted disk, the dust on the near side is silhouetted against the bright inner bulge, drawing crisp, dark lanes, while dust on the far side hides behind that same glow and washes out. The effect is subtle, a matter of which quadrant of the image carries the sharper shadows, but it is decisive, and Hubble's optics were equal to it. The dust lanes told Bird and Buter which edge of NGC 4622 leans toward us. The spectra told them which way the disk sweeps. Put together, the two facts convicted the galaxy. The two strong outer arms are leading. The dominant pattern of this spiral opens into its own rotation, ploughing face first around the disk, the reversed fan blades, the hair streaming into the wind. They announced the result at the American Astronomical Society meeting in January 2002 and a follow-up study in 2007, answering challenges with additional photometric analysis of the near side, reaffirmed the verdict. The wrong-way galaxy was real, and it was the first of its kind confirmed anywhere in the sky. Leading arms were not a new idea, which is part of what makes the case instructive. Theorists had played with them for decades, and the mathematics of gravity permits them. What theory also said, with some confidence, is that disks should erase them quickly. A leading pattern fights the shear of differential rotation instead of riding it, and in simulations such patterns are fragile, temporary arrangements, expected to unwind or dissolve on timescales short compared to a galaxy's life. That is why no one had ever found one. Catching a galaxy in so brief a phase should be either extraordinary luck or a hint that the phase is not as brief as believed, and either option is uncomfortable. Luck is not an explanation, and a longer-lived leading pattern means the models are missing something about how disks hold their shapes. The rule book did not merely lose a rule. It lost the reason the rule was supposed to be safe. So, what happened to this galaxy? The leading suspect is an act of consumption. The Hubble image shows disturbed material near the core, the kind of interior untidiness that a clean, isolated spiral should not have, and it suggests that NGC 4622 swallowed a smaller companion galaxy sometime in its past. A merger delivers new material onto orbits of the eater's choosing, and if the swallowed galaxy came in backward, retrograde to the disk's rotation, its remains would stir the disk against the grain. Simulations show that material on such backward orbits can drive and sustain leading patterns far longer than an undisturbed disk would allow. The counterwinding inner arm, in this story, is the scar of the meal, the visible signature of a dead galaxy's momentum still churning inside the survivor. A close pass by a neighbor, rather than a full merger, can produce similar mischief for a while. But the merger story fits the evidence best, and it carries a fine irony. The galaxy that looks most serene in its portrait may owe its signature strangeness to an act of quiet violence, completed and digested long before we looked. There is one more layer worth holding, and it is the reason this entry sits on a list of mysteries rather than curiosities. Spiral arms, remember, are not objects. They are density waves, traveling patterns of compression that stars and gas drift through, brightening as they pass, the way a traffic jam persists on a highway while every individual car eventually escapes it. A pattern is information, not material, and that is precisely why arms can, in rare circumstances, decouple from the intuition that everything must trail. NGC 4622 demonstrates that the universe's disks can carry information against their own current, at least for a while, and nobody can yet say how long that while is, or how often it happens, or how many other face-on spirals are quietly winding the wrong way behind the perfect camouflage of a flat viewing angle. Remember that this galaxy was caught only because two people spent 10 years cross-examining a subtlety. The sky does not volunteer this information. It waits to be asked precisely. The announcement, it should be said, was not waved through. Extraordinary claims in astronomy draw cross-examination, and the leading arm verdict drew its share. Skeptics proposed that the dust reading might be subtler than it seemed, that a warp in the disk could mislead the geometry, or that the faint inner arm might be an artifact of overlapping structure rather than a true counterwinding pattern. This is how the field is supposed to work, and Bird and Buter answered the way careful workers answer, with more measurement. Their 2007 analysis went back to the disk's light with fresh photometry, testing the near-side determination through independent means, checking whether the arm's colors and star-forming regions made sense under each possible geometry, and the leading arm conclusion survived each test. It is worth being honest about the epistemic state. The case rests on inference, on dust and Doppler and geometry assembled into a verdict, not on some impossible overhead film of the galaxy actually turning. A determined skeptic can still find corners to probe. But the alternative explanations have each required more coincidence than the plain reading, and 2 decades on, NGC 4622 remains the textbook case of leading spiral structure, cited precisely because the proof was so laborious. Suppose you could watch it, though. Suppose you could hang above the disk, with time running 100 million years to the second. An ordinary spiral, viewed this way, would soothe you. The arms sweep back, the pattern turns with a stately lag, everything combed by the current, a weather system in equilibrium. NGC 4622 would look wrong within the first second. The two great outer arms crest forward into the flow, like waves that have decided to break against the tide, and the little inner arm curls back the other way beneath them, and the whole arrangement grinds around its center with the visible tension of a mechanism running against its own gears. Intuition says it must fly apart, and the honest answer of the simulations is that eventually it should. What you are watching, in this imagined time-lapse, is not a stable design, but a long, slow argument between a disk and its history, an argument that began when a smaller galaxy dove in against the spin, and has not yet finished being absorbed. We arrived, with our telescopes, somewhere in the middle of the argument. That is all observation ever gets, the middle of things, and this galaxy makes the fact unusually vivid. There is also a technical wrinkle that dynamicists prize here. Every spiral pattern turns with its own speed, called the pattern speed, which is separate from the speed of the stars that pass through it, and there is usually a special radius, called corotation, where star and pattern move together. Rings in a galaxy often mark these resonant radii, the places where orbits and pattern beat in step and material accumulates, and NGC 4622 is a ringed galaxy, its disk carrying circular structures alongside its contradictory arms. That detail matters, because the rings are like tree rings of the disturbance, a record of where the resonances have parked material. Buter in particular is one of the field's leading catalogers of galactic rings, and in this galaxy, his two specialties collide. The rings and the backward arms belong to one dynamical story, and a full solution would have to derive both together, the resonant clockwork and the reversed pattern, from one initial insult. No published model has yet closed that loop completely, which is a precise way of saying the mystery is still open, not as a slogan, but as an unfinished calculation sitting on the field's desk. The human dimension of the proof deserves its sentence too. The team that cracked the galaxy's geometry included Tash Freeman, an instructor at Bevel State Community College, a 2-year college in rural Alabama, whose name sits on the Discovery alongside the university astronomers and the Space Telescope. Astronomy still has room for that, for a problem so specific and so patient that the decisive contributions come from whoever is willing to stare longest at dust lanes, regardless of the letterhead. And the reward for all that patience was not a new object, but a subtraction. Bird and Buter took away one of astronomy's simplest certainties, the glance that tells you a spiral's spin, and certainty subtracted from science is never quite restored. Every textbook diagram of trailing arms now carries a silent asterisk, and this quiet, plate-shaped galaxy in Centaurus is the reason. Even the galaxy's distance carries a lesson in humility, and it is worth the short detour. You may have noticed the range quoted earlier, somewhere between 100 and 200 million light-years, which is an unusually loose grip for so well-studied an object. The reason is that cosmic distances at this range are inferred, not measured directly. Astronomers read a galaxy's redshift, the stretching of its light by cosmic expansion, and convert it into distance using the expansion rate. But a galaxy also carries its own private motion through space, pulled by neighbors and clusters, and at these ranges that private motion can contaminate the conversion noticeably. Independent distance markers, the standard candles that calibrate the nearby universe, are harder to isolate in a crowded face-on disk. So different methods return different answers, and the honest summary is a range a factor of 2 wide. It changes nothing about the leading arm verdict, which rests on geometry rather than distance, but it is a good reminder of the terms on which all of tonight's knowledge is held. For every galaxy on this list, we know the direction exquisitely and the range approximately, like hearing a voice with perfect clarity from somewhere across a dark valley. We cannot visit it to settle the remaining questions, of course. At 100 million light-years and more, NGC 4622 is as sealed off from our instrument's touch as everything else tonight, a place we interrogate only with geometry and light. Still, however strangely it turns, this galaxy is at least full of stars, a working spiral with a bright core and busy arms, recognizably a member of the family. The next entry on this list cannot say that. The next entry is an enormous rotating disk, heavy with the raw material of 100 billion suns, that has never, in the entire history of the universe, made a single star. Number 7, J0613 plus 52, the galaxy that never made a star. Number 7 on this list begins with a definition, offered in good faith, so that we can watch it fail. A galaxy is a place where gas becomes stars. Strip away every refinement, and that is the working heart of the concept. Gravity gathers hydrogen, hydrogen pools into clouds, clouds collapse and ignite, and the result, multiplied 100 billion times and set spinning, is the shining object the word galaxy has always meant. Every entry so far tonight, however strange, has honored that definition. Malin 1 honors it faintly, Hoag's ring honors it in a circle, NGC 4622 honors it while turning the wrong way. Number 7 does not honor it at all. Number 7 is a galaxy that has never made a single star, and astronomy found it because a telescope was pointed at the wrong place in the sky. The object is catalogued as J0613+52, a name that is nothing more than its coordinates, because there is nothing visible at those coordinates to name. The discovery was announced in January of 2024 at a meeting of the American Astronomical Society by a team from the Green Bank Observatory in West Virginia, led by the astronomer Karen O'Neill. And the project that produced it could hardly have been more routine. The team was conducting a census of gas in several hundred known low-surface brightness galaxies, the same dim class of objects that Malin 1 made famous at the start of tonight's list. Their instrument for the survey was actually 3 instruments, 3 of the great radio dishes of the world. The Green Bank Telescope in West Virginia, the largest fully steerable telescope on Earth. The Arecibo dish in Puerto Rico, before its cables failed and its platform fell in December of 2020. And the Nancy radio telescope in France. Between them, the survey measured the cold hydrogen in about 350 separate galaxies, one pointing at a time, building an unglamorous and valuable table of numbers. Cold hydrogen, remember, sings at a radio wavelength of 21 centimeters. The signal comes from a tiny rearrangement inside each atom, the electron flipping its spin, a transition so improbable that a given atom performs it roughly once in 10 million years. No laboratory quantity of hydrogen could ever be heard this way. But a galaxy is not a laboratory quantity. Gather billions of solar masses of the stuff, and the whisper multiplied by the mass becomes a clear broadcast, and a radio dish the size of a stadium can hear it across hundreds of millions of light years. Map the broadcast, and you weigh the gas. Read the spread of its frequencies, and you learn how the gas is moving. It is one of astronomy's most reliable measurements, honed over 70 years, and on the night in question it required only that the telescope be aimed at the galaxy on the list. A word about the instrument, because the discovery is unimaginable without it. The Green Bank Telescope stands in a valley in Pocahontas County, West Virginia, inside the National Radio Quiet Zone, 13,000 square miles of country, where radio transmissions are legally restricted so that the dishes can listen. Within the innermost zone, even Wi-Fi and microwave ovens are policed, and staff drive diesel trucks because spark plugs whisper in radio. The dish itself is a marvel of odd engineering, 100 meters across, its surface made of more than 2,000 aluminum panels, riding on actuators that continuously reshape the mirror against gravity's sag as it tilts. It is the largest moving structure on land that can point at any spot in its sky. All of that machinery, all of that legislated silence, exists to catch whispers like the one this story turns on, signals a billionth of the strength your phone handles every second. Radio astronomy is the discipline of hearing almost nothing perfectly, and Green Bank is one of its great ears. The history rhymes too. Arecibo and Nancy, the survey's other 2 dishes, were both built in the 1960s, and the 21-centimeter line they were all listening for was first detected in 1951 by Harold Ewan and Edward Purcell with a horn antenna hanging out a window at Harvard. A technique 3 generations old, refined and refined, was about to stumble onto one of the newest kinds of object in astronomy. It was not. The coordinates entered for one observation were wrong, off by a fraction of a degree, and the 100-meter dish of the Green Bank Telescope, a structure taller than the Statue of Liberty, swung with its usual precision to an address where nothing lives. The patch of sky it settled on was blank, an empty interval between catalogued objects, the kind of place surveys pass over by design because there is nothing there to survey. Understand what should have happened next. The spectrum should have come back empty, a flat line of instrument noise, and the error would have been caught, logged, mildly regretted and corrected, one more small human stumble in the long bookkeeping of observational astronomy, remembered by no one. Instead, the blank sky answered. A clean, strong, well-formed hydrogen signal rose out of the noise, the unmistakable 21-centimeter voice of billions of solar masses of cold gas, coming from a place where every optical survey ever conducted showed nothing at all. No smudge on the plates. No faint entry in any catalogue. Darkness, as far as photography was concerned, and the darkness was broadcasting. The team checked the pointing, found the error, and understood that the mistake itself was the discovery. Somewhere along that wrong line of sight, roughly 270 million light-years out, there was a massive, invisible reservoir of hydrogen that nobody had ever suspected, because nobody had ever had a reason to look. Careers in astronomy are spent choosing targets wisely. This target chose itself, through a slip in a coordinate field, and it turned out to be the kind of object the field had been debating for decades without ever holding a clean example. Because here is what the follow-up work assembled. The gas at J0613+52 is not a shapeless cloud. Its signal has the double-horned profile that radio astronomers know the way a doctor knows a heartbeat, the signature of a rotating disk, gas swinging toward us on one side and away on the other, in a stable, organized circulation. The mass of that gas comes out around 2 billion solar masses, a reservoir comparable to what the entire Milky Way carries. And organized rotation implies something more. Gas does not discipline itself into a stable spinning disk without a deep well of gravity to hold it, far more gravity than the gas alone supplies, which means the disk almost certainly sits inside a massive halo of dark matter, the same invisible scaffolding that holds every proper galaxy together. Take the inventory. A dark matter halo. A rotating disk. Billions of suns of raw fuel. That is the complete parts list of a galaxy, every component present and functioning. And in the deepest optical images anyone has yet taken of that spot, there are no detectable stars. The machine is assembled, plugged in, and has never once been switched on. A galaxy is a place where gas becomes stars, we said. Here is a place that has everything except the becoming. How does a galaxy fail to begin? The team's leading interpretation makes the object stranger, not tamer. The gas appears to be spread too thin. Star formation is a threshold phenomenon. Hydrogen must pool densely enough for clouds to cool and collapse before gravity can win its local battles, and everywhere in J0613+52, the surface density of the gas seems to sit below that critical line. Malin 1, at the start of tonight, showed us the same physics operating at the margins, a giant forming stars at a trickle. This object is the physics taken to completion, a disk where the trickle never started. And the second half of the interpretation explains how such a delicate arrangement could survive. J0613+52 is profoundly isolated. It sits in a quiet corner of the sky, with no near neighbors, no companions to tug at it, no cluster environment to squeeze its gas, nothing passing close enough to shock the disk into collapse. Galaxies, as a rule, grow up in crowds, and the crowding is half the story of their growth. Collisions and near misses compress gas, ignite starbursts, and turn reservoirs into cities of light. This disk appears to have spent the entire history of the universe alone, its fuel spread evenly and undisturbed, waiting for a push that never came. That is why the Discovery team reached for a large word, primordial. If the picture is right, J0613+52 is not a broken galaxy, or a stripped galaxy, or a faded galaxy. It is an unstarted galaxy, a surviving specimen of the stage every galaxy passed through before its first stars, preserved for something approaching 13 billion years by sheer solitude. Astronomy has fossils of many kinds: old stars, ancient globular clusters, the relic radiation of the Big Bang itself. It has never securely held this particular fossil, a dark disk from before starlight, intact and still turning. If confirmation holds, we are looking at the childhood photograph of every galaxy in the sky, including our own, taken not 13 billion years ago, but now, because one specimen somehow never grew up. The word "if" is doing honest work in those sentences, and the team has been careful to say so. Astronomy has been burned by dark galaxy claims before, and the cautionary tale has a name: Virgo He 21. In the 2000s, radio astronomers reported a starless hydrogen cloud in the Virgo cluster, with the dynamical signature of a dark galaxy, and the announcement drew enormous attention, and then the skeptics went to work. The Virgo cluster is a violent place, thick with galaxies whose close encounters routinely tear off long streamers of gas, and closer analysis argued persuasively that Virgo He 21 was exactly that, a tidal streamer ripped from a neighboring galaxy, a piece of debris mimicking a disk. The candidate collapsed into a cautionary footnote. That history is precisely why the isolation of J0613+52 matters so much. There is no neighbor for it to have been ripped from. The nearest significant galaxies are too far away to have donated 2 billion solar masses of coherent, rotating gas. The streamer explanation, the one that killed the last great candidate, has no purchase here. This is the first dark galaxy candidate, discovered far from any scene of a crime. Still, the title remains provisional, and the path to confirming it runs through work that is underway as this list is being spoken. Deeper optical imaging pushing far below the thresholds of existing surveys to hunt for the faintest possible whisper of starlight across the disk. High-resolution radio mapping to trace the structure of the rotation in detail and confirm that the disk is a disk, with the mass distribution a genuine galaxy requires. There are two ways the verdict can land, and the remarkable thing is that both are records. If no stars appear, the object is confirmed as the first true dark galaxy, a class of one, the found fossil of the pre-stellar universe. If a ghost of a stellar population does appear, then J0613+52 becomes instead the faintest galaxy ever discovered, an object whose stars are so few and so dim that all the world's telescopes had missed them. Heads, a new kind of object. Tails, a record holder. It is a rare mystery that cannot resolve into something ordinary, and this appears to be one of them. Drift out there for a moment, since tonight is for drifting. You are suspended inside J0613+52, somewhere in the body of the disk. The darkness around you is total in a way no place in our galaxy can manage. In the Milky Way, darkness is always relative, always a matter of shielding, a cave, a closed room, the shadow of a world, with starlight forever leaking in at the edges. Here, there is nothing to leak. No star has ever risen in this galaxy's sky, in 13 billion years of nights. The hydrogen streams past you in its grand, patient circulation, cold beyond any winter, a river wider than the orbit of the sun, flowing around a center no eye could find, because no light has ever marked it. Hold a hand in front of your face and there is no difference. And yet this is not empty space. Gravity holds you inside a definite structure, a place with an inside and an outside, a rotation, a history, an address. If you struck a single match, its light would be the first light the galaxy had ever contained, and it would sail outward through the dark gas forever, announcing nothing to no one. The universe has kept this room dark since before the continents of Earth existed, and it would have kept the secret indefinitely, except that someone, 400 million trillion miles away, typed the wrong coordinates into a telescope. There is even a modest role in this story for the listener's own intuition. Ask yourself what the odds were. The sky, measured in patches the size of that pointing error, contains millions upon millions of addresses, and the overwhelming majority of them hold nothing within the survey's reach. A random miss should have found a random emptiness. Instead, it found the one kind of object that emptiness could actually be hiding, which suggests, gently but firmly, that such objects may not be rare at all. When a single throw of a dart hits a hidden target, either the throw was miraculous or the wall is covered with targets you cannot see. Astronomers, as a professional habit, do not believe in miracles of aim. Sit with the human half of that for a moment, because it is the emotional center of this entry. Karen O'Neill has spent a career studying the dim outskirts of the galaxy population, choosing targets with care, writing proposals, defending telescope time, doing the deliberate work of a deliberate science. The survey that produced this discovery was exactly such work, 350 careful pointings at 350 chosen objects. And the find of the survey, possibly the find of a career, came from pointing number 351, the one nobody chose. Somewhere in a control room log at Green Bank, there is a small error that no one would ever have elected to make, and it may have handed astronomy its first galaxy from before starlight. The lesson is not that care is wasted. The care is what made the accident legible, because only a team that knew exactly what a normal signal looked like could recognize an impossible one instantly. But it is a lesson about the shape of discovery. The universe is under no obligation to place its treasures along our chosen lines of sight, and what we know still depends, sometimes, on where we were not trying to look. Astronomers have a blunt statistic for objects like this: the mass-to-light ratio, the amount of matter present for every unit of light emitted. The Sun, by definition, scores 1. A typical galaxy, counting its dark matter, scores in the tens. The dimmest dwarf galaxies known, the dark matter-dominated wisps orbiting the Milky Way, reach into the thousands, and those numbers are considered astonishing. J0613 plus 52, with billions of solar masses and no detected light at all, has a mass-to-light ratio that is, in the optical, effectively infinite. Any starlight eventually found will convert that infinity into some enormous finite number, but the present situation is worth stating plainly. This is the darkest rotating structure ever identified, an object whose entire measurable existence is gravitational and radio frequency, with photography contributing exactly nothing. 4 centuries of astronomy were built on the visible sky. Here is a galaxy-sized demonstration of how much universe that sky was never going to show us. And what of its future? Isolation preserved this disk, and isolation shows no sign of ending. No large neighbor is inbound. No cluster will sweep it up on any foreseeable timescale. Left alone, the gas will continue its slow rotation, thinning at its edges, radiating its faint hydrogen whisper for billions of years to come, perhaps for the rest of cosmic history. There is something almost restful in that thought. Nearly every object in astronomy is a story of transformation, collapse, ignition, explosion, merger, decay. This one is a story of pure continuation, a held breath that has lasted 13 billion years and may simply never be released. Then again, the universe is long and gravity is patient. Some distant age could still deliver the nudge, a wandering dwarf galaxy, a slow tide from the larger structure it faintly feels, and the old fuel would finally pool and collapse, and a galaxy's worth of first stars would ignite in a sky that had never held one. If that ever happens, it will be the latest first dawn in the history of the universe, and by then, no telescope of ours will exist to see it. There is a last, quiet thought to carry out of this entry. If one such object exists, hidden in the blankness between catalogued galaxies, found only by a misfire, then the obvious question is, how many more are out there? Radio surveys cover the sky far more sparsely than optical ones, and a dark disk broadcasts only in wavelengths we sample thinly. The blank patches of the sky, the boring intervals every survey skips, may hold an entire quiet population of unstarted galaxies, each one invisible to photography by nature rather than by distance. Nobody can yet attach a number to that possibility. It simply stands open, like a door discovered in a familiar wall. A galaxy that never lit its fuel sits at one extreme of tonight's inventory. The next entry on this list sits at the other, a galaxy burning brighter than any object of its kind ever measured, 350 trillion suns of light pouring out of a single dusty engine, and the mystery is that it may be destroying itself in the act. Number 6, W2246. The most luminous galaxy in the universe. Number 6 on this list carries a name that is pure catalogue bureaucracy, WISE J224607.56 -052634.9, and astronomers, being human, shortened it to W2246. Behind that filing code stands a record that has not fallen in over a decade of searching. W2246 is the most luminous galaxy known in the universe. It pours out roughly 350 trillion times the light of the sun. Numbers that size stop meaning anything unless you run them slowly, so let us run this one slowly. In a single second, this one galaxy releases about as much energy as our sun emits in 10,000 years. Every second, another 10,000 solar years of output. It outshines the entire Milky Way, all of its several hundred billion stars added together, some 10,000 times over. If you could compress our galaxy's whole population of suns into a single furnace and then build 10,000 such furnaces, you would have approximately 1 W2246. And here is the first turn of the mystery. Point the finest optical telescope on Earth at this record-breaking beacon, and you will see almost nothing. The most luminous galaxy in the universe is nearly invisible, because virtually none of its light escapes as light our eyes were built for. It reaches us as heat. The story of its discovery is the story of a small, unglamorous spacecraft that outperformed every expectation. In December of 2009, NASA launched the Wide-Field Infrared Survey Explorer, a space telescope with a mirror just 40 centimeters across, smaller than the instruments in many amateur observatories. WISE was not built to stare deeply at anything. It was built to scan, sweeping the entire sky in infrared light, month after month, cataloging everything that glows with heat. By the time its survey was done, it had logged some 750 million sources, asteroids and cool stars and dusty galaxies beyond counting. Sifting that mountain of data, astronomers noticed a rare and peculiar class of object, galaxies almost absent from visible light surveys but burning ferociously in the far infrared, as if all their brilliance had been laundered through smoke. The team called them hot, dust-obscured galaxies, and because scientists cannot resist an acronym, hot DOGs, they are genuinely scarce. For every 3,000 quasars WISE could find, it found roughly one hot DOG. In 2015, a team led by Chow Wei-Tsai measured the distances and energy budgets of the most extreme of them and made the announcement. One object, at a redshift of 4.6, was the most luminous galaxy ever measured. Its light had been traveling for about 12.5 billion years. We see W2246 as it was when the universe was barely more than 1 billion years old, a tenth of its present age, and it was already outshining everything. It is fair to ask how anyone is sure of numbers like these, and the answer is the ordinary machinery of careful astronomy. The distance rests on spectroscopy from the great ground-based observatories, which caught the fingerprint lines of the galaxy's light stretched to 4.6 times their laboratory wavelengths, a redshift that the expansion history of the universe converts into those 12.5 billion years of travel. The luminosity rests on adding up the galaxy's output across the full spread of wavelengths, the bolometric budget, dominated overwhelmingly by that infrared glow, with WISE's all-sky calibration anchoring the arithmetic. Each step is standard. Only the total is outrageous. And the record has been stress-tested in the way records are, by rivals. Other hyperluminous candidates have been proposed, some initially reported as brighter, and one by one, the challengers have been revised downward on closer inspection, their light amplified by gravitational lensing or their distances reconsidered. W2246, checked and rechecked for over a decade, has kept the crown, which is part of why astronomers treat its extremity not as a measurement error, but as a fact demanding explanation. What powers such an engine? Not stars. No population of stars, however furious, arranges itself into what the measurements show. Buried at the center of W2246 is a supermassive black hole whose mass runs to billions of suns, and it is feeding at close to the fastest rate physics permits. Matter spiraling toward a black hole does not fall straight in. It backs up into a whirling disk, and friction within that disk heats the gas to millions of degrees until the disk blazes with more light than thousands of galaxies. Astronomers call such an object a quasar, and quasars are the brightest sustained phenomena in the universe. W2246 is a quasar with a peculiarity. It is wrapped, cocooned, smothered in dust, a shroud so thick that the quasar's visible and ultraviolet blaze cannot escape directly. Instead, the dust absorbs that light, warms to around 450 Kelvin, hotter than a kitchen oven, and re-radiates the energy outward as infrared heat. That is why a 40-centimeter heat-scanning telescope found what generations of great optical observatories had missed. The galaxy is a furnace viewed through its own chimney smoke. Nothing about the furnace is visible. Everything about the smoke is. There is a speed limit involved here, and it deserves its own moment because it governs the entire story. When matter falls toward a black hole and heats, its radiation pushes back on the infalling material. The harder the engine feeds, the brighter it burns, and the brighter it burns, the more its own light shoves the next meal away. At a certain brightness, the push of the radiation balances the pull of gravity, and feeding can no longer accelerate. Astronomers call that ceiling the Eddington limit, after the English astrophysicist Arthur Eddington, who worked out the balance a century ago for stars. For a black hole of a given mass, the limit sets the maximum sustainable appetite, and W2246 appears to be operating at or near that ceiling, running its engine against the physics of light itself. Think about what that means for the record. This is not merely the most luminous galaxy we have found. It may be close to the most luminous a galaxy of its kind can be, an object pressed against a universal boundary, the way the deepest note of an organ is set not by the builder's ambition, but by the length of air itself. Records in astronomy usually fall to better instruments. Records set by physical limits are a different kind, and this one has stood since 2015. To hold the luminosity in the hand a little longer, try one more translation. If you replaced our sun with a source shining at W2246's full output, Earth would not be scorched or sterilized. Those words are too small. The planet would be gone, its rock vaporized and driven outward as glowing gas, and the same would be true for every planet of every star for a very long way. A galaxy's worth of worlds cannot exist near such a thing in comfort. And yet, spread across a whole galaxy and buried under dust, all of that fury reduces, at our distance of 12.5 billion light-years, to a smudge of warmth that no human eye, at any telescope, will ever see directly. The most violent furnace in the catalogue is also one of the gentlest presences in our sky, a fact you can carry as a kind of lullaby. Distance is the universe's own volume control, and it is turned, for us, nearly all the way down. The record alone would earn W2246 a place in the catalogues, but not necessarily on this list. What earns it a place among the mysteries is what the gas is doing, and for that we owe the Atacama Large Millimeter Array, ALMA, 66 precision radio dishes, standing on a plateau 5,000 meters up in the Chilean Andes, one of the highest and driest places on Earth, where the atmosphere is thin enough to let millimeter waves through. In 2016, astronomers used ALMA to map a particular whisper from W2246, the radiation of ionized carbon atoms drifting in the galaxy's interstellar gas. Ionized carbon is a tracer, a dye in the water. Map it, and you map the motion of the galaxy's gas. In a normal galaxy, such a map shows order, rotation, lanes, the traffic patterns of a functioning system. The map of W2246 showed something else. Turbulence. Everywhere. Gas churning at hundreds of kilometers per second, not in one jet, not in one outflowing cone, not at one wounded spot, but across the entire body of the galaxy at once, in every direction, uniformly. The interstellar medium of the whole galaxy is boiling. And the conclusion the team drew is the sentence at the heart of this entry. The black hole's radiation is stirring the galaxy so violently, driving so much energy into the gas from the inside, that W2246 may be in the process of blowing away its own cocoon, unbinding its own interstellar medium. The most luminous galaxy in the universe appears to be tearing itself apart. Then, in 2018, ALMA delivered the second half of the picture, and it reads like dark comedy. W2246 is not alone. It sits at the center of a small crowd, a multiple merger system, and the imaging revealed streamers of dust and gas, faint bridges, connecting the giant to three separate smaller companion galaxies. These are feeding lines. Material is being pulled out of all three neighbors and is flowing along those bridges into the central galaxy, and the longest of the streamers stretches on the order of 25,000 light-years, a river of galactic material longer than the distance from Earth to the center of the Milky Way. The total mass caught mid-transfer in those bridges is comparable to the mass of the companion galaxies themselves. They are not being nibbled. They are being drained. So assemble the full portrait now. Here is a galaxy consuming three of its neighbors simultaneously, funneling their substance inward, feeding a black hole of billions of solar masses at the limit of its appetite, which in turn pours out 350 trillion suns of energy, which in turn churns the entire galaxy's gas into a boil that threatens to blow the whole dusty edifice open. The inflow feeds the fury. The fury fights the inflow. It is a system eating and detonating at the same time, a fire drawing fuel toward itself with one hand and scattering it with the other. Spare a thought for the three companions, because their fate is the least mysterious thing in this entry and somehow the most affecting. They are ordinary small galaxies, each with its own history, its own generations of stars, presumably its own planets beyond counting. Their misfortune is proximity. On timescales of hundreds of millions of years, the drain will complete, the bridges will close, and all three will be absorbed entirely, their stars scattered through the halo of the giant, their identities erased from every future map. Nothing will mark that they existed except, perhaps, faint streams of stars that a sufficiently patient future astronomer, in some galaxy we cannot name, might one day trace backward like handwriting. Galactic cannibalism is common. Our own Milky Way is threaded with the star streams of dwarfs it consumed long ago, and Andromeda is inbound for a merger with us in about 4.5 billion years. What is uncommon is catching the meal mid-swallow, in triplicate, at the table of the brightest eater in the known universe. That contradiction is why astronomers suspect we have caught something brief and pivotal, a phase transition in the life of a giant galaxy. The theoretical picture runs like this. Great galaxies and their central black holes grow together, and the growth spurts happen in mergers, when colliding galaxies pour gas toward the center. For a while, the feeding is hidden, the new quasar buried under the very dust the merger delivered, blazing only in infrared. A hot dog, in other words, may simply be a quasar in its cocoon stage. But the stage cannot last. Either the black hole's radiation eventually wins, blowing the shroud away and revealing a naked, visible quasar to the universe, or the violence chokes off the feeding, the engine starves, and the whole system dims toward quiet. W2246 appears to be balanced at exactly that decision point, and the turbulence ALMA measured looks like the deciding argument in progress. The rarity fits the story. One hot DOG per 3,000 quasars is about right if the cocoon phase is short, a flicker in galactic time. We are watching, 12.5 billion years after the fact, a few million years of a galaxy's life that will determine its next billion. The observations have kept coming because record holders attract telescopes. In 2026, the James Webb Space Telescope turned its infrared instruments on W2246 and mapped the structure of its dust in new detail, and the results suggested that much of the extreme infrared glow escapes along preferred directions, out the poles of the system, where the shroud is thinnest. That refines the model of the furnace and its chimney, without dethroning any of the mystery. The central questions stand. How does a black hole grow to billions of solar masses within the universe's first billion years, fast enough to be caught mid-feast this early? That problem, the problem of overweight black holes too early in cosmic history, has only sharpened as Webb has found more distant examples, and W2246 remains one of its most extreme exhibits. Which way will the balance tip, the blowout or the choke? The light that would tell us is still in transit and will be for billions of years. On the wall of cosmic history, this galaxy is a single frame of a film whose next scene was decided over 12 billion years ago, and we are permanently forbidden from seeing it. One more detail belongs in the record, a human one. The hot DOG class was identified not by an algorithm alone, but by people willing to chase the least photogenic objects in the data, sources that showed us nothing in the visible sky and refused to match any familiar template. It would have been easy to set them aside as glitches. Instead, teams spent years of follow-up on mountaintop spectrographs, pinning down what they were, and the reward was an entire hidden population of the universe's most powerful engines, wearing blankets. Every catalog contains a column of misfits. Somewhere in today's surveys, the next W2246 is presumably sitting in such a column, unremarkable in every band we favor, waiting for someone to take the ugly data point personally. Distance seals the entry, as it seals every entry tonight. 12.5 billion light-years of travel time means we see this galaxy in the universe's early morning, and the object itself, whatever it became, has long since finished becoming it. Perhaps it is a serene giant elliptical now, its black hole quiet, its dust long gone, indistinguishable from 1,000 others. Perhaps it tore its shroud off and reigned for an age as one of the great visible quasars. The heat that brushes Webb's detectors tonight left the galaxy when the Milky Way itself was still assembling out of fragments, and no message, no probe, no observer from here will ever close that distance to check the ending. Everything about W2246 is too much. Too bright, too hungry, too turbulent, too early. The next mystery on this list is its perfect opposite, a galaxy defined not by excess, but by absence. And what it is missing is the one ingredient the universe is supposed to guarantee. It is missing most of itself. Number 5. NGC 1052 DF2, the galaxy missing its dark matter. Number 5 on this list requires us to talk about the 95% of the universe this list has so far only gestured at. So let us do that properly, and then meet the galaxy that threw the subject into chaos. For nearly a century, astronomy has known that galaxies weigh far more than they appear to. Fritz Zwicky saw it first in the 1930s, clocking the speeds of galaxies in the Coma cluster and finding them moving far too fast for the visible matter's gravity to hold them. Vera Rubin and Kent Ford made it inescapable in the 1970s, measuring the rotation of spiral galaxies and finding their outskirts orbiting as fast as their interiors, which visible matter cannot arrange. The resolution, tested now against decades of evidence, is that every galaxy sits inside a vast halo of invisible material, dark matter, outweighing the stars and gas 5 or 10 times over, and in some galaxies far more. Nobody has ever detected a particle of it. Yet it is not a decoration on modern cosmology. It is the load-bearing wall. In the standard picture, dark matter collapsed first in the young universe, and its gravity gathered the ordinary matter that became stars, which is to say that galaxies exist because dark matter called the meeting. A galaxy without dark matter, in that picture, should be close to a contradiction in terms, a building without a foundation, standing anyway. In March of 2018, the journal Nature published a paper about a dim smear of stars called NGC 1052 DF2, and the paper's title said, "The impossible thing plainly." A galaxy lacking dark matter. The galaxy was found by an instrument that deserves its own documentary. The Dragonfly telephoto array, conceived by Peter van Dokkum of Yale and Roberto Abraham of the University of Toronto, is not a traditional telescope at all. It is a rack of commercial Canon telephoto lenses, the same 400mm lenses sports photographers haul along sidelines, ganged together on a mount in New Mexico and aimed at the sky as one. The design sounds like a prank and is actually a precision solution. Big mirrors scatter a whisper of light around every bright source, and that scattered veil drowns the faintest, most diffuse structures in the sky. Camera lenses with modern nanostructured coatings scatter far less, so an array of them, stacked, can photograph objects a great observatory smears into its own glare. Dragonfly began in 2013 with 3 lenses. It grew to 48. Its specialty is exactly the phantom class of galaxy this list keeps returning to, objects large in extent and low in light, and in the field around the elliptical galaxy NGC 1052, about 65 million light-years away in the constellation Cetus, it photographed a specimen that would make it famous. DF2, the second entry in that field's Dragonfly catalogue. A galaxy roughly the footprint of the Milky Way, holding about 1/200th of its stars, so sparse you can see straight through its body, distant galaxies shining between its stars like lights through a curtain of gauze. It helps to picture what an ultra-diffuse galaxy actually is, because the class was only named in 2015 and it still surprises people. Take the Milky Way's footprint, a disk 100,000 light-years wide. Now remove all but half of 1% of its stars and spread the survivors evenly so that no bright center forms, no arms, no bar, just an even, dying ember glow across the whole area. From inside such a galaxy, the night sky would be nearly starless, a scattering of lonely lights with enormous darkness between them, and the galaxy itself would cast no band of light across its own sky, nothing like our Milky Way arch. From outside, the object is barely an object. Long exposure images show a pale oval, smooth as fog, and the fog is the galaxy. Astronomers had glimpsed such things for decades at the edge of detectability, but Dragonfly's clean optics turned a suspicion into a population, dozens in a single field, then hundreds. The universe, it emerged, is generously stocked with galaxies built at 1% opacity, and almost everything about them, their origins, their contents, their life stories, was unknown as recently as a decade ago. DF2 was about to make one of those unknowns famous. Sparse galaxies by themselves were no longer news by 2018. What made DF2 detonate was the weighing. Scattered around the galaxy are globular clusters, dense, luminous knots of hundreds of thousands of stars each, orbiting the galaxy the way bees orbit a hive. 10 of them were bright enough to serve as tracers. Measure their speeds, and the spread of those speeds tells you the mass of the thing they orbit. The same logic Zwicky applied to coma nearly a century ago, applied now in miniature. Van Dokkum's team took spectra with the Keck telescopes in Hawaii, and the clusters came back moving with a spread of merely about 8 kilometers per second. 8. A commercial airliner cruises at around a quarter of that speed. For a galaxy of DF2's extent, a normal dark matter halo would drive those clusters to 30 kilometers per second or more. Run the arithmetic on 8, and the total mass of DF2 comes out approximately equal to the mass of its visible stars alone. The books balance with nothing hidden. The foundation is not merely small. To the precision of the measurement, it is absent. Now, the paradox, and it is one of the loveliest in modern astronomy. You might expect a galaxy without dark matter to comfort the skeptics, the physicists who suspect dark matter is not a substance at all, but a misreading of gravity, the position held by theories of modified gravity. The opposite is true. If dark matter is really a modification of gravity's own law, then the modification must apply everywhere, to every galaxy, without exception, because gravity does not take days off. Every galaxy should show the anomaly. A galaxy that fails to show it, a galaxy whose stars move exactly as slowly as visible matter alone predicts, is a galaxy where the supposed law of modified gravity has switched off, which a law cannot do. But if dark matter is a substance, a physical something that usually accompanies galaxies, then it is allowed to be separable. A galaxy could, through some violence of history, lose its dark matter, or be assembled without it. Absence is only possible for ingredients, not for laws. And so the galaxy missing dark matter became, perversely, one of the strongest arguments that dark matter is real, a substance you can strip, an entry the universe can leave off a ledger. Keep that phrase within reach tonight. The universe, it turns out, keeps incomplete ledgers, and the incompleteness is informative. Pause on the measurement itself, because its delicacy is easy to skate past. 8 kilometers per second is not a number you read off an image. Each globular cluster's speed comes from its spectrum, from the collective starlight of its hundreds of thousands of stars, shifted by the Doppler effect a few thousandths of a percent. The shift must be measured to a precision of a kilometer or two per second in objects so faint that gathering enough light takes hours on a 10-meter mirror, and then the individual speeds must be combined into a spread, with the statistics of small numbers handled honestly, because 10 traces is not many. The team's critics pressed exactly there, on whether 10 objects can anchor so large a claim, and the response over subsequent years was to add traces, to re-observe, to check the galaxy's own diffuse starlight for its internal motions. The numbers held within their stated uncertainties. This is what a modern astronomical controversy actually looks like from the inside. Not rival press releases, but rival error bars, argued over line by line at conferences and in referee reports for years. The universe does not surrender its ledgers casually. The astronomical community responded to all this in its traditional manner, which is to say, it reached for knives. Extraordinary results attract scrutiny in proportion to their importance, and DF2's importance was enormous. The sharpest attack targeted the distance. Everything in the mass argument leans on how far away the galaxy is, because distance sets the true brightness of the stars, and the true brightness sets how much stellar mass there is for the dynamics to account for. A team led by Ignacio Trujillo argued the galaxy sat much nearer than claimed, around 42 million light-years rather than 65. Pull DF2 that much closer, and its stars dim, its stellar mass shrinks, the ratio rearranges, and the missing dark matter reappears in the books. The anomaly would die quietly, another cautionary tale about cosmic distances. Van Dokkum's team answered with the bluntest instrument available, time on the Hubble Space Telescope, 40 orbits of it, enough imaging to resolve the brightness of the galaxy's red giant stars, whose peak luminosity acts as a standard reference. The method is worth a sentence of admiration. Red giant stars, the swollen late stage of sun-like stars, reach a well-defined ceiling of brightness set by the physics of their cores, the same ceiling everywhere in the universe. Resolve a galaxy's individual red giants, find the brightness at which their population tops out, compare that observed ceiling to the known true ceiling, and the distance follows almost like reading a ruler. It requires resolving single stars in a galaxy tens of millions of light-years away, which is exactly the kind of task Hubble was built for, and almost nothing else can do. 40 orbits of the telescope's time, a substantial grant of one of astronomy's scarcest resources, went into settling one number, about one faint smudge. The result pinned DF2 at about 72 million light-years, if anything slightly farther than the original claim. The anomaly survived its execution date. And while the argument raged, it doubled. A second galaxy in the same field, DF4, weighed by the same method, showed the same impossible lightness. Two foundationless buildings, standing side by side. Two of a kind is no longer a fluke, and it demands a mechanism, and the mechanism proposed in 2022 is the kind of idea that sounds like fiction until you notice how much it explains. Van Dokkum's team pointed out that DF2 and DF4 are not randomly placed. They sit along a remarkably straight line of faint galaxies in the NGC 1052 field, a trail, 7 to 11 objects long depending on how you count, aligned like droplets along a wire. The proposal runs as follows. Around 8 billion years ago, two gas-rich dwarf galaxies collided head-on at hundreds of kilometers per second. Their dark matter, which interacts through gravity alone and cannot crash, passed through itself and sailed on, carrying whatever stars came along. Their gas did what gas does. It collided, compressed, stopped, and was left behind at the crash site, strung along the collision axis. And from that orphaned gas, in the following ages, condensed a chain of new galaxies, every one of them born without dark matter, because their birth material was precisely the fraction of the ancestors that the dark matter could not follow. The scenario is a miniature of the famous bullet cluster, where two colliding galaxy clusters visibly separated their gas from their dark matter on the grandest scale. Here the same physics, scaled down 1,000-fold, would have written its signature as a line of ghost galaxies. The idea made a testable promise. If the trail is a crash site, more of its members should be missing their dark matter too. In April of 2026, that promise came due. Astronomers reported a third galaxy along the alignment, weighed and found wanting in exactly the predicted way, a third orphan on the trail. The bullet dwarf story is not proven, and its critics remain in print, but a hypothesis that names its next discovery in advance and then receives it is doing the one thing science respects most. As of the making of this video, the count of confirmed dark matter-free galaxies in that field stands at 3, all on one line, all consistent with a single ancient accident. If the picture holds, we are looking at the debris field of a collision that predates the Sun, preserved because the debris happens to be made of galaxies. Two small mysteries ride along inside the big one, and honesty requires them both. First, DF2's globular clusters are themselves odd, unusually large and roughly twice as luminous as globulars anywhere else in the surveyed universe, as if the same strange birth that skipped the dark matter also supersized the star clusters. No one knows why. Second, a later study found DF2's body to be a calm, regular stellar disk with no signs of tidal disturbance, which quietly undermines the rival explanation that a close pass by the big neighboring elliptical stripped its dark matter in the recent past. Strippers leave stretch marks. This galaxy has none. Meanwhile, the modified gravity camp has counter-arguments of its own, invoking the external field effect, a subtlety in which a galaxy's internal dynamics can be muted by the gravity of its neighbors, and the debate over whether that rescue works has itself filled papers. Follow the chain far enough down, and you arrive at the honest bottom. This dim smudge in Cetus is a live argument about what most of the universe is made of, conducted by a few dozen people measuring airliner speeds across 72 million light-years, and it is not finished. Stand inside DF2 for a moment before we leave it, because its sky teaches the lesson better than its numbers do. You are on a world orbiting one of its scattered suns. The night above you is nearly empty, a few hundred stars where Earth's sky holds thousands, and no glowing river of galaxy crosses it, because your galaxy is too sparse to draw one. But the strangeness is not what is missing from the sky. It is what is missing from underfoot, from everywhere, from the invisible accounting of your world's motion. On Earth, an astronomer measuring our galaxy's spin discovers the great discrepancy, the unseen 5/6, and builds a century of physics chasing it. Your astronomers would measure and find no discrepancy at all. Their galaxy would balance perfectly, visible mass explaining visible motion, a tidy universe with no missing majority. They would have no reason to imagine dark matter exists. The great question that has organized 100 years of our cosmology simply would not arise there. Two civilizations, two honest sets of measurements, two different universes inferred, and the difference is an accident of galactic birth. It is a quiet warning about all knowledge assembled from inside a single home. And there is a practical edge to all of it, far from Cetus. Deep underground on Earth, in mines and mountain laboratories, detectors of exquisite sensitivity have waited decades for a dark matter particle to brush an atomic nucleus, and they have caught nothing yet. Each null result tightens the allowed hiding places. In that climate, some physicists drift toward the modified gravity camp, and the existence of galaxies like DF2 is one of the strongest observational ropes holding the field to the substance picture. A separable ingredient can be missing here and abundant there. A law cannot. The dim smudge and the underground silence are two ends of one question, and at present, the smudge is arguably doing the heavier lifting. A galaxy with no dark matter is one kind of scandal, an entry missing from the cosmic ledger. But the very same instrument, the rack of camera lenses in New Mexico, found the ledger's other impossible entry, and it is next. The same astronomer, the same faint class of galaxy, and the opposite affliction. The next object on this list appears to be almost nothing but dark matter, a Milky Way's worth of gravity, wearing a veil of stars so thin it took until 2015 to notice, and the argument over what it actually is has split astronomy for a decade. Number 4. Dragonfly 44, the galaxy that is almost entirely dark. Number 4 on this list is the other side of the ledger, and the symmetry is almost too neat for non-fiction. The same rack of camera lenses in New Mexico, the same astronomer at Yale, the same ghostly class of galaxy, and the exactly opposite affliction. NGC 1052 DF2, our number 5, is a galaxy that appears to have no dark matter at all. Dragonfly 44, our number 4, is a galaxy that appears to be almost nothing else. It drifts in the Coma cluster, about 330 million light-years away, in the constellation of Coma Berenices, and for a few years after its weighing, it carried one of the most arresting descriptions in the history of astronomy. A galaxy of 1 trillion solar masses, the heft of the entire Milky Way, of which everything visible, every star, every cluster, every wisp of gas, accounted for roughly 1 part in 10,000. 99.99% dark. A shadow the size of our galaxy, wearing a dusting of stars the way a mountain wears a late spring snow. The setting matters, so let us place it. The Coma cluster is one of the great gravitational metropolises of the nearby universe, a swarm of over 1,000 galaxies bound together, their members swinging through the cluster's collective gravity at speeds of thousands of kilometers per second. It is also, fittingly, historic ground for this exact subject. In 1933, it was the galaxies of Coma whose excessive speeds led Fritz Zwicky to infer, for the first time, that some unseen mass must bind them, the observation that began the entire dark matter story. 90 years later, the same cluster hosts the darkest galaxy candidates ever found. The story, after a century of wandering through laboratories and satellite data, came home to the place it started. Coma is also, for a fragile galaxy, a terrible neighborhood. Galaxies there do not drift in peace. They plunge through the cluster's hot gas, they swing past one another, they cross the deep center where tides are fiercest, and anything loosely held gets stripped, shredded, and scattered into the intra-cluster haze. Astronomers can see the victims, streams and plumes of orphaned stars threading the cluster. So when the Dragonfly Array surveyed Coma in 2014 and 2015 and revealed dozens of enormous, dim, cobweb galaxies as wide as the Milky Way, but thousands of times fainter, the immediate puzzle was not their dimness. It was their survival. Objects that tenuous, made only of their visible parts, should not endure the cluster's violence. Tissue paper does not survive a storm. Yet there they were, dozens of them, then hundreds as the counting continued, roughly 800 candidates in Coma by later censuses. Their persistence was itself a measurement. Something invisible was holding each of them together, some hidden mass lending structural strength that their starlight could not explain. The question was how much, and the biggest, boldest specimen in the field was the natural place to ask. That specimen was catalogued as Dragonfly 44. The survival argument can be made precise, and it is worth doing, because it converts a metaphor into a scale. Every object moving through a cluster has what dynamicists call a tidal radius, the distance from its center beyond which the cluster's differential pull overwhelms the object's own grip. Anything outside its tidal radius is not really its anymore. The cluster is already in the process of taking it. For a galaxy made only of its visible stars, spread as thinly as Dragonfly 44 spreads them, the tidal radius in Coma's inner regions would cut deep inside the visible body. The outskirts we photograph should be streaming away, drawn into tails, and repeated orbits through the cluster should have combed the whole object into wreckage long ago. Instead, the galaxy's outline is smooth, symmetric, and intact. Working backward, the intactness sets a floor under the hidden mass. However much dark matter the recount debate ultimately assigns, it cannot assign too little, or the galaxy we photograph could not continue to exist where we photograph it. The object's sheer persistence is a weighing scale that no spectroscopic dispute can entirely reset. Asking cost a remarkable amount of photons. In 2016, Pieter van Dokkum's team took the question to the Deimos spectrograph on the 10-meter Keck 2 telescope in Hawaii and accumulated 33.5 hours of exposure on this single object. Understand what that allocation means. Time on a 10-meter telescope is among the scarcest commodities in science, scheduled in half-nights, fought over by hundreds of proposals, and a galaxy so faint spends that time grudgingly, yielding its spectrum photon by photon. 33.5 hours was one of the longest stares Keck had ever given a single galaxy. The purpose was to measure the random internal speeds of Dragonfly 44's stars, the velocity dispersion, the same style of weighing we have now seen twice tonight, applied not to orbiting clusters, but to the galaxy's own blended starlight. The number that came back was 47 kilometers per second. For the amount of starlight present, that number is enormous. Stars milling at 47 kilometers per second, about 105,000 miles per hour, require the gravity of roughly 1 trillion solar masses to stay bound, and Dragonfly 44's stars supply perhaps 1/100% of that. The team also counted the galaxy's globular clusters in Hubble imaging and found an entourage of about 94, the retinue of a giant, when a galaxy of its faintness should keep a handful. Two independent lines, the dispersion and the cluster count, pointed the same direction. This was not a puffed-up dwarf. This was a Milky Way mass halo in which star formation had, for some reason, barely happened at all. The team published the result, and the phrase went around the world. A galaxy made of 99.99% dark matter. The Milky Way's dark twin. It is worth understanding what those 33.5 hours actually brought, because the measurement is subtler than pointing and weighting. A galaxy's blended starlight carries absorption lines, dark fingerprints at wavelengths where the atmospheres of its stars swallow their own light. If every star stood still, the lines would be knife-sharp. Because the stars mill about, each one's contribution is shifted slightly by its own motion, and the summed lines smear into soft valleys. The width of that smearing is the velocity dispersion. For a galaxy as dim as Dragonfly 44, the entire spectrum is a faint grey whisper on the detector, and the smearing must be disentangled from the instrument's own blurring, from the sky's emission, from cosmic ray strikes, from every artifact a long exposure collects. Night after night on the mountain, the signal accumulated a few photons at a time, and the final number, 47 kilometers per second, emerged from a statistical fit with error bars attached. Those error bars are where the next decade of argument would live. The point of describing all this is not procedural. It is that the sentence, "This galaxy is 99.99% dark matter," rests, physically, on the measured softness of shadows in a whisper of light gathered over a month of nights, and knowing that changes how one should hold the sentence. Sit with the implication for a moment, because it is genuinely strange. In the standard picture of galaxy formation, a halo of 1 trillion solar masses is a winning lottery ticket. It should gather gas by the tens of billions of suns, ignite sustained star formation, build a disk or a great spheroid, and light up brightly enough to be catalogued by every survey since the photographic plate. The universe cashes that ticket essentially every time, which is why halos of that size are reliably wrapped in bright galaxies. Dragonfly 44, on the 2016 numbers, was a trillion solar mass halo that had converted less than 1,000th of its allowance into stars, a jackpot winner living in the dark, a failure of galaxy formation on the grandest possible scale. Theories scrambled to accommodate it. Perhaps ferocious early feedback, the winds of the first supernovae, blew out its gas before the galaxy could properly begin. Perhaps it was a failed giant, a Milky Way that misfired. Each explanation strained something. None of them was absurd. The object simply sat there in coma, dim and implacable, insisting that the menu of possible galaxies was larger than anyone had written down. Imagine living there, briefly, since the imagining sharpens the physics. You orbit one of Dragonfly 44's scattered suns, under a night sky even emptier than DF2's, a few forlorn stars over an otherwise perfect black. But your world's astronomers, unlike DF2's, would discover almost the opposite universe. Measuring the drift of their sparse neighbors, they would find motions wildly too fast for the visible stars to explain, a discrepancy not of the familiar factor of 5 or 10, but, on the original numbers, of 10,000. Their cosmology would be dark matter cosmology from its first measurement, not as a refinement, but as the entire subject. The visible universe, for them, would be a rounding error on reality, a thin, luminous impurity in a world of pure gravity. Between number 5 and number 4 tonight, the universe has staged the same lesson twice, with the signs reversed. What a civilization concludes about existence depends on which galaxy it happens to wake up inside, and the range of available conclusions is wider than anyone suspected a decade ago. Then came the recount, because in science, the recount always comes, and this is the part of tonight's entry that is really about how knowledge is made. From 2019 onward, other teams went back over the evidence, and the most persistent challengers were Timur Seyfulahi, Ignacio Trujillo, and their collaborators, some of the same names that had pressed hardest on DF2's distance. Their re-examination of the Hubble imaging found far fewer globular clusters than originally reported, roughly 20 rather than 94. Once stricter criteria distinguished true clusters from background contamination. And reanalyses of the spectroscopy argued the velocity dispersion had been overestimated, with later measurements, including some from Van Dokkum's own group, trending lower into the low 30s of kilometers per second. Rerun the arithmetic with 20 clusters and a gentler dispersion, and Dragonfly 44 transforms. The ratio of dark to visible falls from 1 in 10,000 to something like 1 part visible in 300. Still profoundly dark. Still dominated by unseen mass. But no longer a Milky Way twin, no longer a cosmic outlier, roughly in line, the challengers argued, with what a large dwarf galaxy of its type ought to carry. On their numbers, the most famous ghost in coma is not a failed giant at all. It is a normal citizen of a strange class, promoted by measurement error. If counting globular clusters sounds like it should be trivial, consider the actual task. At 330 million light-years, a globular cluster, an object of a few 100,000 stars packed into a ball perhaps 100 light-years wide, appears as a single point of light, indistinguishable at a glance from a faint foreground star in our own galaxy or a compact background galaxy shining from billions of light-years beyond. The counter must work by statistics, selecting candidates by exact brightness, color, and size profile, estimating how many imposters of each type should contaminate the field, and subtracting. Every threshold in that chain is a judgment call, defensible in more than one place, and moving a threshold moves the census. 94 and 20 are not two observations of different skies. They are two defensible readings of the same photographs. Anyone who has recounted anything under pressure, votes, inventory, money, knows the uneasy truth that counting is only simple when the things counted are cooperative. At the faint edge of the sky, nothing cooperates. Van Dokkum's camp pushed back, defending the dispersion measurement, contesting the cluster recount, and the exchange has continued across the literature for years, civil, technical, and unresolved. In 2022, a major science magazine could still accurately title its retrospective on the object, The Enduring Mystery of the Dragonfly 44 Galaxy. Both sides agree the galaxy is dark matter dominated. They disagree by a factor of about 30 on how dark, and that factor is the difference between an interesting specimen and a crisis for galaxy formation theory. It is worth being precise about what the disagreement is made of. It is made of counting faint dots, deciding which smudges are clusters and which are distant galaxies photobombing the frame. It is made of extracting a velocity spread from spectra where the signal is a whisper over the noise, where choices about which pixels to trust shift the answer by kilometers per second. There is no negligence anywhere in it. There are only measurements at the edge of the possible, made by careful people, disagreeing. The universe does not round its answers to the precision of our instruments, and at the faint frontier, our instruments are still the limiting reagent of truth. And that is the emotional center of this entry, more than any number. Peter van Dokkum found the galaxy missing its dark matter and the galaxy made of it, with the same instrument he helped invent, within a few years of each other, twin discoveries at the two ends of a spectrum nobody knew existed. Then he watched, in real time, as colleagues took his most famous number apart, recounted his clusters, refit his spectra, and published a much smaller mystery in its place, and the field's honest answer to who is right remains, a decade after the first announcement, pending. There is no villain in that story. That story is the scientific method working exactly as designed, with its gears exposed. The public tends to meet science as a finished product, polished conclusions in textbooks, and tonight's number 4 is science as a live process, a decade-long disagreement about the composition of a galaxy, conducted in error bars, still open at this hour. If you want to know what the honest state of human knowledge about dark matter looks like, it looks like Dragonfly 44, a smudge in coma that is either ordinary or revolutionary, depending on how you count 20 dots. The origin stories deserve their own minute, because each one predicts a different universe, and the population of ghosts will eventually vote. The first story is the failed giant. A halo destined for greatness assembles its trillion solar masses, begins gathering gas, and then, in its violent adolescence, its own first burst of supernovae detonates with such coordinated fury that the remaining gas is blown clear of the galaxy before it can settle, leaving a giant skeleton with a dwarf's wardrobe. If that story is common, the darkest, ultra-diffuse galaxies should carry giant-sized retinues of globular clusters, forged in the brief, bright beginning, which is exactly why the cluster recount matters so much. The second story is the spun-up dwarf. Halos are born with different amounts of rotation, and a dwarf galaxy in an unusually fast-spinning halo will spread its modest stars across a giant's footprint, thin as breath on glass. No failure involved, just geometry. That story predicts ordinary dark matter totals under the big dim disks. The third story is the tide-puffed dwarf, a normal, compact galaxy kneaded and inflated by repeated gravitational passes inside the cluster, heated until its stars balloon outward. That story predicts stretch marks, tails, and asymmetries, at least in some specimens, and it struggles with ghosts found drifting far from any cluster, where no tide has ever worked. The honest current assessment is that the class of ultra-diffuse galaxies is probably a shared costume worn by several different creatures, and Dragonfly 44 is the one specimen every version of the story is required to fit, which is precisely why its contested numbers matter beyond its own patch of coma. Either way the count resolves. Note what survives it. Take the most conservative published numbers, and you still hold a galaxy with the footprint of the Milky Way, less than 1/100th of its light, surviving for billions of years inside one of the roughest gravitational environments in the nearby universe, held together by 100 times more matter than it shows. The class it leads, the ultra-diffuse galaxies, number in the hundreds in coma alone, and their origin remains genuinely unsettled, with failed giants, spun-up halos that spread their stars too thin, and tide-puffed dwarfs all still in contention, each explaining part of the population and failing another part. Whichever origin story wins, the universe is demonstrably manufacturing galaxies that are mostly gravity and barely light at industrial scale, and it kept that fact from us until the 2010s because we had not built the right kind of eye. And there is no visiting coma to settle any of it. At 330 million light-years, the light we are reading tonight left Dragonfly 44 before the first dinosaurs, and every conclusion we ever draw about it will be drawn from that old, faint, arguable whisper. What would settle it? More light, mostly, from bigger eyes. The 30-meter class of telescopes now rising, with collecting areas an order of magnitude beyond Keck's, could measure the galaxy's dispersion with error bars small enough to starve the argument, and could take spectra of individual candidate globular clusters, converting the contested statistical count into a verified membership list, cluster by cluster. Wide, deep space-based surveys will meanwhile find ultra-diffuse galaxies by the thousands across many environments, turning a debate about one specimen into a census of a species. The likeliest ending, as with most scientific fights, is not a dramatic verdict, but a quiet dissolve, a future review paper noting that the population's properties are now well measured and that the early controversy reflected the heroic difficulty of the first attempts. The people who spent their nights on the mountain, on both sides, will have been how that ending got written. And the stakes reach past coma into the standard model of cosmology itself. The reigning theory, cold dark matter with a cosmological constant, makes its cleanest predictions about the dark halos, how many form at each mass, how they cluster, how they grow. Its persistent troubles have always lived at small scales, in the counting of dwarf galaxies and the insides of faint halos, exactly the territory the ultra-diffuse galaxies now illuminate. If Dragonfly 44 is truly a trillion solar mass halo nearly empty of stars, then halos of a given mass can wear wildly different amounts of light, and every survey that infers the invisible universe from the visible one inherits a new layer of doubt. If instead the recounted, modest numbers hold across the class, then the ghosts slot neatly into theory as inflated dwarfs, and the standard model sails on. A single factor of 30 hanging on 20 dots sits between those two readings of the cosmos. Zwicky, who coined the very phrase dark matter while studying this same cluster, and who was famously combative about how slowly his field absorbed inconvenient measurements, would have recognized the situation instantly. The cluster he used to open the question is now hosting the argument about how strange its answer is allowed to be. Whatever Dragonfly 44 is made of, though, it at least keeps its own center. Its stars, however few, mill around a shared middle in the ordinary way, and nothing essential has been thrown out of the house. The next galaxy on this list cannot say that. It is one of the largest galaxies in the known universe, the bright central giant of an entire cluster, and by every rule in the book it should keep, at its exact center, one of the largest black holes in existence. Astronomers have pointed the best X-ray observatory ever flown directly at the spot. The spot, so far as anyone can tell, is empty. Number 3, a 2261 BCG, the galaxy missing its black hole. Number 3 on this list begins with the most reliable partnership in extragalactic astronomy, so that we can appreciate the shock of finding it broken. Every large galaxy, as far as decades of measurement can establish, keeps a supermassive black hole at its center. The Milky Way keeps Sagittarius A star, 4.3 million solar masses, its orbiting stars tracked so precisely that the work earned the 2020 Nobel Prize in Physics. Andromeda keeps a black hole of over 100 million solar masses. The giant elliptical Messier 87 keeps the 6.5 billion solar mass monster, whose shadow the Event Horizon Telescope photographed in 2019, the first portrait of a black hole in history. And the partnership is not casual. The mass of the central black hole tracks the properties of its host galaxy so tightly, across thousands of measured systems, that astronomers speak of coevolution, galaxy and black hole growing together across cosmic time, each regulating the other. Big galaxy, big black hole. It is as close to a law as extragalactic astronomy possesses. Which brings us to the galaxy where the law appears to have failed. It is fair to ask how firm the law really is, since the whole entry leans on it. The relation astronomers trust most links a black hole's mass to the stirred speeds of the stars in its galaxy's central bulge, the velocity dispersion again, our recurring instrument tonight. Measure both quantities across galaxies where the black hole's mass can be pinned directly, from orbiting stars, from swirling gas disks, from the natural masers that orbit some nuclei like radio beacons, and the points fall along a tight line spanning a factor of 1,000 in mass. The bigger and hotter the bulge, the bigger the hole, with remarkably little scatter. That line was hammered out through the 2000s from dozens of galaxies, and it is why an astronomer can look at a giant they have never weighed and state its black hole's mass within a factor of a few, the way a doctor estimates a stranger's heart size from their chest. The prediction for this galaxy is not a guess. It is the confident output of the field's most tested relation, which is exactly why the empty result lands so hard. About 2.7 billion light-years away, toward the constellation Hercules, lies the galaxy cluster Abell 2261, and at its heart sits its brightest cluster galaxy, catalogued as A2261 BCG. Brightest cluster galaxies are the aristocracy of the universe. They grow at the gravitational center of their clusters, feeding for billions of years on every smaller galaxy that falls within reach, and they become the largest stellar systems in existence. This one spans roughly 1 million light-years, about 10 times the diameter of the Milky Way, and holds on the order of 10 trillion solar masses in stars, gas, and dark matter. Apply the scaling laws that work everywhere else, and its central black hole should be spectacular, somewhere between 3 billion and as much as 100 billion solar masses, which at the upper end would rank among the largest black holes in the known universe. The telescope time was allocated, the searches were made, and the results came back. Nobody can find it. A word on the address, because the cluster itself is a landmark. The Abel Catalogue, compiled by George Abel in 1958 from photographic survey plates and extended after his death, lists the richest galaxy clusters visible from Earth, and it remains the field's basic gazetteer, 4,000 entries deep. Abel 2261 earned extra fame in the 2010s as one of the 25 clusters selected for Hubble's CLASH program, a survey using massive clusters as natural telescopes. A cluster's gravity bends the light of whatever lies behind it, magnifying background galaxies into arcs and smears, and in Hubble's deep portraits of this cluster you can see them, thin blue threads of far more distant galaxies, stretched around the great central elliptical-like reflections in the shoulder of a spoon. There is a pleasing irony in that. The cluster whose central galaxy cannot produce its own black hole is one of astronomy's favorite gravitational instruments, its mass so vast and well-behaved that researchers use it to study everything except the one thing it seems to be missing. The first hint that something was wrong arrived with Hubble imaging in 2012, analyzed by a team including Mark Postman of the Space Telescope Science Institute and Todd Lauer of the National Optical Astronomy Observatory. They were measuring the galaxy's core, and the core came out wrong in two ways. First, its size. The flat, evenly lit central region of A2261 BCG spans about 10,000 light-years, the largest galactic core ever measured, 3 times larger than the cores of comparable giants. For scale, you could set the entire visible disk of a small galaxy inside this one's core and lose it. Second, its emptiness. In a normal giant, the starlight climbs steadily toward a bright, dense center, a peak marking where the black hole holds court amid the densest crowd of stars. Here, the profile rises and then simply flattens, a plateau of starlight with no summit, as if the center of the galaxy had been scooped out with a spoon and smoothed over. Stranger still, the brightest concentration of stars in the whole system is not even at the middle. It sits offset, about 2,000 light-years from the geometric center, a displaced heart beating in the wrong part of the chest. Cores like this are not unknown, and their standard explanation is itself a story worth hearing. When two giant galaxies merge, their central black holes sink toward the middle of the combined system and pair into a binary, two monsters orbiting each other. That binary then acts as a gravitational slingshot. Any star that strays close is whipped away at enormous speed, carrying off a sliver of the binary's energy, and over millions of years the process ejects the central crowd outward, star by star, excavating a core. Astronomers call it core scouring, and the amount of missing light in a scoured core normally tracks the mass of the black holes that did the digging. But A2261 BCG's core is outsized even for that mechanism, its missing stars amounting to tens of billions of solar masses of absent light, and scouring alone does not explain the flatness, the offset knot, or what came next. Because the natural response to an oversized, scooped-out core is to go find the black hole that dug it, and this is where the story turns into a missing persons case. Even a quiet supermassive black hole is rarely perfectly silent. Gas drifts onto it, and in falling gas heats to millions of degrees and glows in X-rays, a pilot light betraying the furnace even when the furnace is banked. In work culminating around 2021, a team led by Kayhan Gultekin of the University of Michigan pointed the Chandra X-ray Observatory, the sharpest X-ray eye ever flown, at A2261 BCG for 100,000 seconds of fresh exposure, stacked with 35,000 seconds from the archive. They examined the geometric center of the galaxy. No source. They examined the offset knot of stars. No source. They examined 3 additional compact clumps of stars near the core, any of which might secretly host the fugitive. No source, though one clump's stars were too faint to rule on conclusively. They checked the site of old radio emission, the fossil of some past outburst of nuclear activity, which observations date to roughly 50 million years before the light we now receive departed. Nothing is glowing there now. Wherever a black hole of 3 to 100 billion solar masses ought to be quietly feeding, the best X-ray observatory in history recorded darkness. Hold the strangeness of that in place. This is not a small failure to detect a small thing. On the scaling laws, the missing object outweighs the Milky Way's black hole by a factor of 1,000 or more. It is the largest single object known to be missing anywhere in astronomy, and its absence revives the phrase we coined 2 entries ago. The universe keeps incomplete ledgers. At number 5, the missing entry was a galaxy's dark matter. Here, it is the galaxy's central engine, and this time the books do not merely fail to balance. They point, actively, toward a suspect and an exit. Because there is a mechanism, predicted by general relativity itself, that can throw a supermassive black hole out of its own galaxy. Return to the binary at the center of the merged giant. The 2 black holes spiral together, radiating gravitational waves, and in their final moments, they merge in a burst of space-time ripples carrying, briefly, more power than all the stars in the observable universe combined. If the 2 holes' masses and spins are arranged symmetrically, the waves depart evenly and the merged hole stays put. But if the arrangement is lopsided, and especially if the spins are tilted just wrong, the waves are beamed preferentially in one direction and momentum conservation does the rest. The merged black hole recoils the other way, like a rifle against a shoulder. Simulations of these gravitational wave kicks find that ordinary configurations produce recoils of hundreds of kilometers per second, and rare, finely mistuned configurations produce superkicks approaching 5,000 kilometers per second. 5,000 kilometers per second exceeds the escape velocity of even a giant elliptical galaxy. Run the sequence in your mind. 2 giants merge. Their black holes pair, scour the core flat, and finally collide. The merged monster, kicked at thousands of kilometers per second, tears free of the galaxy's grip and departs into intergalactic space, naked, dark, and permanently gone, dragging with it only whatever stars orbited closest, a compact swarm that theorists call a hyper-compact stellar system, riding the runaway like foam on a wave. The oversized core, the offset knot, the 50-million-year-old radio fossil marking the engine's last known address, and the X-ray silence, every clue in this galaxy is consistent with that story. One of the compact clumps near the core was examined as exactly such a getaway vehicle. The verdict on it, like so much tonight, is pending. The radio fossil deserves its own moment, because it is the closest thing the case has to a timestamp. When a supermassive black hole feeds actively, it drives jets and inflates lobes of radio-emitting plasma, and when the feeding stops, the lobes do not vanish. They drift, expand, and fade, their radio spectrum aging in a calculable way, the high frequencies dying first like the treble going out of an old recording. Radio observations of A2261 BCG's vicinity find exactly such aged emission, and reading its spectrum backward dates the last significant activity to roughly 50 million years before the light we receive departed the galaxy. 50 million years is, on galactic clocks, remarkably recent, perhaps 1% of the time since the galaxy assembled. Whatever silenced this nucleus did so almost within memory. That timing suits the ejection story uncomfortably well. A merger completes. The binary tightens. The engine flares one last time on the infalling debris of the process, and then the kick carries it away, leaving the fresh radio smoke hanging in the room it just left. None of that is proof. All of it is consistency, and consistency accumulating in one direction is how missing persons cases begin to close. It must be said plainly that the ejection is a hypothesis, not a conviction. There is a tamer possibility that the black hole is present and simply fasting with unprecedented discipline, accreting so little that even Chandra cannot see its pilot light. Black holes can be quiet. Our own Galaxies is famously abstemious. But a giant at a cluster's center swims in gas, and total silence from so large an object in so rich an environment strains the tamer story badly. No recoiling supermassive black hole has ever been confirmed anywhere in the universe. Candidates exist, quasars oddly displaced from their galaxies, emission lines racing at suspicious speeds, but each has alternative readings, and the field is still waiting for its first clean case. A 2261 BCG is the leading crime scene precisely because it offers the complement, not a fleeing suspect, but an empty room, the first galaxy where the absence itself has been measured this carefully. Confirming the ejection would be a landmark, the first direct evidence that gravitational wave recoil operates at the supermassive scale, that the universe really does, on rare occasions, fire its heaviest objects across intergalactic space, like shells from a gun. The future may adjudicate. The LISA Space Observatory, planned for the 2030s, will hear supermassive black hole mergers directly in gravitational waves, kicks and all, and every such detection will tell us how often the universe pulls this trigger. Consider, too, what an escaped black hole actually becomes, because the fate is stranger than the escape. A black hole in flight emits nothing of its own. Once its stolen swarm of stars fades and disperses across the ages, and once it leaves behind the gas of its former home, it will accrete almost nothing, glow at almost nothing, and become as close to a perfectly undetectable object as nature manufactures, billions of solar masses of curvature moving through the dark between clusters. The universe would hide it in plain nothing. There is one faint hope for such fugitives, the same trick the cluster itself performs. Mass bends light, and a wandering giant black hole drifting across our line of sight to background galaxies would announce itself through gravitational lensing, warping and brightening what lies behind it in a signature no ordinary object mimics. Surveys of the coming decades, monitoring billions of sources, could in principle catch such an event. Nobody holds their breath. The volume is enormous, the fugitives are few, and the alignment must be nearly perfect. But it is worth knowing that the ejection story, if true, populates intergalactic space with a thin scattering of the heaviest invisible bullets in existence, and that the only way any of them will ever be seen again is by the accident of something shining behind them. Stand at the center of that galaxy for a moment, in the middle of the great flat core. Around you, in every direction, the sky is powdered with the light of a million light-year giant, stars beyond counting, evenly spread, with no bright heart anywhere. In any normal giant galaxy, this spot would be the most dangerous address in the system, the seat of a monster, wrapped in the blaze of the densest starlight and the glow of infalling gas. Here there is only the level, democratic shine of a scoured plateau, 10,000 light-years of politely spaced suns. If the recoil story is true, then somewhere out in the darkness beyond this galaxy's edge, a black hole heavier than 10 billion suns is falling silently through intergalactic space, wearing its stolen swarm of stars, unfindable perhaps forever. And this room, the largest throne room ever built by gravity, will stay exactly like this, kingless, for the rest of cosmic time, because the one object that could rebuild the center has left, and nothing so large will ever fall in to replace it. A missing engine is a mystery of place, an absence at an address. The final two galaxies on this list are mysteries of time, and they will carry us to the edge of what can be seen at all. The first of them is a pinwheel, perfect and serene, photographed in an era of cosmic history when pinwheels were not supposed to be possible, a piece of architecture standing calmly in the middle of a construction site 3 billion years into the age of chaos. Number 2, BX 440 TWO, the spiral that formed too soon. Number 2 on this list looks, at first glance, like the least mysterious object of the night. It is a spiral galaxy, a graceful two-armed pinwheel with a bright center, the single most familiar shape in astronomy, the form your hand draws when anyone says the word galaxy. The mystery is not the shape. The mystery is the date. This galaxy's light left it 10.7 billion years ago, when the universe was roughly 3 billion years old, and at that hour of cosmic history, by everything astronomy understood, pinwheels were not yet possible. Finding it, one researcher involved remarked, was like finding a finished piece of architecture standing in the middle of a construction site. The galaxy's catalog name is Q2343 BX442, BX442 for short, and it carries a companion superlative that has held for over a decade. It is the earliest grand design spiral galaxy ever confirmed, a full epoch ahead of its time. To understand why its existence startled anyone, you need to know what the early universe's galaxies were actually like, and the honest word for them is storms. In the first few billion years, galaxies grew fast and ate violently. Cold gas poured onto them along the filaments of the cosmic web, not as a gentle rain but as dense, penetrating streams. Collisions came constantly, neighbor tumbling into neighbor. The disks that managed to form were thick, hot, and churning, their internal motions so turbulent that gas clouds the size of whole star-forming regions bobbed and lurched like debris in floodwater. Photograph such galaxies, as Hubble did in its deep fields, and you see the era plainly. Clumps, chains, tadpoles, train wrecks, irregular knots of furious star formation, beautiful in their way, and utterly unlike the serene wheels of the modern sky. Grand design spirals, the two-armed showpieces like Messier 51 or Messier 81, are creatures of a later, calmer universe. The pattern that defines them is a density wave, an organized compression sweeping through the disk, with stars and gas drifting through the moving pattern, slowing and brightening as they pass, the way cars drift through a traffic jam that itself crawls along the highway. And a density wave is a delicate machine. It requires a disk that is dynamically cold, meaning its stars and gas follow calm, circular, disciplined orbits, thin and settled and dominated by orderly rotation. Stir such a disk violently and the wave cannot propagate. The pattern smears and dies within a single rotation. Asking for a grand design spiral 3 billion years after the Big Bang is asking for cathedral acoustics in the middle of a rock slide. It is worth knowing that spiral arms were a genuine scientific crisis once before, in our own backyard, because the history illuminates the present case. When astronomers first understood differential rotation in the early 20th century, they realized that material arms made of a fixed set of stars, could not survive. The inner disk laps the outer disk, and any material pattern should wind up like thread on a spindle, wrapping tighter and tighter until it blurs away within a few 100 million years. Yet the sky is full of spirals billions of years old. That contradiction, the winding problem, stood open for decades, until Chia Chow-lin and Frank Shu proposed in 1964 that the arms are not made of particular stars at all. They are waves, patterns of compression through which stars and gas continually pass, patterns that rotate at their own speed, independent of the material. The traffic jam, not the cars. Density wave theory rescued the modern spiral, at the price of those demanding conditions we have already listed, the cold, thin, orderly disk that lets a wave propagate cleanly. So when BX 442 presented a grand design pattern in a hot, thick, disordered disk, it was not merely violating a rule of thumb. It was reaching back and reopening a solved problem, presenting the winding crisis's old question in a new tense. The machinery that explains every spiral in the modern sky does not obviously run in that era's conditions, and there the pattern is anyway. One distinction sharpens the claim, and it costs a single sentence. Spirals come in grades. Most are flocculent, their arms patchy and fragmented, fleece rather than form, and such ragged structure can arise locally, patch by patch, without any galaxy-wide organization. Grand design is the rarer, stricter grade. Two dominant arms coherent across the entire disk, a single organized pattern from center to rim, and it is the grade that demands the delicate, disk-wide density wave. Even in today's calm universe, only about one spiral in 10 manages it. BX 442 is not a marginal case, scraped past a definition. It is the full, strict architecture in the one era that should least afford it. Nobody was looking for one. David Law, then at the University of Toronto, and Alice Shapley of the University of California, Los Angeles, were conducting a Hubble Space Telescope imaging survey of 306 star-forming galaxies at that epoch, chosen from a field on the sky named for the background quasar Q2343, whose light had been used to select and study the foreground population. The survey's purpose was ordinary and valuable, a census of shapes in the era of chaos. 305 of the galaxies obliged the textbooks. They were the expected clumps and wrecks and irregulars, the universe's adolescence photographed in bulk. One image did not oblige. Frame after frame in the analysis, one object kept its composure, a symmetric disk with two arms wrapping a bright center, a grand design spiral in an epoch that was not supposed to make them. One pinwheel in 306 galaxies, a fraction of a percent, sitting in the data like a typographical error in an otherwise clean ledger. The team's first instinct, and this is worth dwelling on because it is the discipline of the field in miniature, was to disbelieve it. The likeliest explanation for a spiral where no spiral belongs is that there is no spiral, that two unrelated galaxies at different distances happen to overlap on the sky, their combined light mimicking arms around a core, a chance projection fooling the eye. Distinguishing a true disk from an imposter requires more than a picture. It requires motion. So Law and Shapley took the question to the Keck Observatory on Mauna Kea and its instrument Osiris, an integral field spectrograph, a device that does something cameras cannot. Rather than one spectrum of the whole object, it takes hundreds of spectra at once, one for each small patch across the galaxy's face, producing a map in which every position carries its own velocity. To sharpen the view through Earth's blurring atmosphere, they used the observatory's laser guide star system, firing a beam into the upper air to create an artificial star whose flicker the telescope's deformable mirror reads and corrects hundreds of times per second. The result was a velocity map of an object 10.7 billion light-years away, sharp enough to answer the question. If BX 442 were two galaxies in costume, the map would show two unrelated velocity systems, discontinuous, incoherent. It showed a single continuous rotating disk, one side approaching, the other receding, the arms riding a coherent circulation about 50,000 light-years wide, enormous for its era. The spiral was real. The paper ran in the journal Nature in July of 2012. And with the imposter eliminated, the real problem stood up. The same velocity map that confirmed the rotation also measured the disk's internal turbulence, and the turbulence was enormous, entirely typical of its violent era. BX442 is not a time traveler from the calm future, a modern disk somehow finished early. It is a storm-era galaxy, hot and churning, with exactly the internal violence that should make a grand design pattern impossible, and it is wearing one anyway. That is the mystery in its purest form. The galaxy does not evade the rule. It violates the rule while visibly possessing all the properties that make the rule apply, order and chaos coexisting in a single measured object, and no appeal to bad data available, because the same observation certified both. Look closely at the portrait, and the era shows through the elegance in one revealing way. The arms of BX442 are not drawn in the fine, filigreed detail of a modern spiral, whose star-forming regions dot the arms like beads. They are drawn in coarse, blazing strokes. The clumps of star formations strung along its arms are enormous, far larger than anything in today's pinwheels, single knots containing the star-making output of entire modern galactic neighborhoods, burning with the ultraviolet fury of thousands of newborn giant stars at once. It is the same design executed in a heavier hand, a cathedral built from boulders rather than bricks, and it reminds you that the underlying disk really does belong to the violent early universe. Nothing about the galaxy's raw material is modern. Only the arrangement is, which is precisely the wrong way around for comfort, since material is easy to explain and arrangement is the mystery. The proposed resolution has a suspect, and the suspect is small. Just beside the great disk sits a dwarf companion galaxy, a modest object of a few percent of BX442's mass, close enough to matter. Gravity from a passing or orbiting companion can ring a disk like a struck bell, exciting a two-armed spiral response, even in a disk too hot to sustain one on its own. The modern sky offers a famous example of the mechanism. Messier 51, the Whirlpool galaxy, owes the crispness of its celebrated arms to the small companion tugging at its edge. The Discovery team ran simulations of the encounter, and the simulations could indeed raise a transient grand design pattern in a turbulent early disk, with one proviso. The pattern is temporary. In the models, it survives on the order of 100 million years before the disk's violence shakes it apart, and 100 million years, against the 10.7 billion of look-back time, is a flicker, about 2% of the interval between that era and this one. If the companion story is right, the Hubble survey did not photograph a stable object. It photographed a moment, a brief chord struck on a turbulent instrument, caught during the note. Follow that arithmetic one step further, and it forks into two possibilities, both interesting. Either the survey was extraordinarily lucky, catching a 100 million year phenomenon in a sample of a few hundred galaxies, odds that make statisticians frown. Or such transient spirals were not rare at all, flickering into existence and dissolving, again and again, all across the early universe, an entire hidden regime of galactic behavior living in the gaps between our snapshots, of which BX442 is simply the specimen that happened to be mid-flicker when our photons left. The second reading quietly rewrites the era. The construction site, it suggests, kept assembling and disassembling cathedrals the whole time, and the wrecks we photograph are punctuated by brief, unrecorded intervals of order. A universe that improvises structure billions of years ahead of schedule, holds the shape for a geological moment, and lets it go. The James Webb Space Telescope has since deepened the theme. From its first deep fields onward, Webb has reported more disks, more order, and more spiral-armed structure at high redshift than pre-Webb theory anticipated, settled-looking galaxies turning up earlier and more often than the storm first picture predicted. The adjustment is ongoing and healthy, models of gas cooling and disk settling being tuned against the new census. In that light, BX 442 has changed roles. It was a freak. It is becoming a forerunner, the first hard, spectroscopically confirmed case of early order, the object that broke the assumption first and now anchors the reconsideration. Records of the deep past are like that. They begin as anomalies and end as the first entries of a new chapter, and the difference is only how much company they eventually acquire. Hang above that disk for a moment, 3 billion years after the beginning of everything. Below you turns a wheel of light, 50,000 light-years across, its two arms traced in burning blue knots, each knot a nursery of thousands of giant stars, the whole pattern sweeping around a golden center. It would be beautiful from any era, and from this era, it is impossible, and you can see the impossibility if you watch closely. The disk seethes. Clouds the size of constellations heave and lurch through the arms, the orderly lanes wobbling like a road drawn on water, everything trembling with the era's violence. And still, the great two-armed shape holds, sweeping its pattern through the chaos, the way a melody survives a noisy room. Off to one side hangs the small companion, the suspected bell ringer, a smudge of borrowed importance. If the models are right, the shape below you is temporary, in the way a rainbow is temporary, a structure the conditions are painting rather than a thing the galaxy owns. Wait 100 million years, and the melody will lose the room. The arms will shake apart into the general storm, and the universe will keep the appointment quiet for 10 billion more years, until a survey on a small blue planet develops the one photograph it ever sat for. The name deserves a footnote before we leave it, because it tells you something about how the deep universe gets mapped. BX 442 is not named for itself. The designation belongs to a survey of the field around the quasar Q2343, a brilliant background beacon whose light astronomers use to probe and select the galaxies floating in front of it. The BX code marks a color selection category, a filing bin for star-forming galaxies at that particular depth of time, and 442 is simply its number in the bin. The earliest confirmed spiral in the universe is catalogued, in effect, as an annotation in the margin of someone else's quasar study. The deep sky is mapped that way more often than not, in fields named for whatever shines brightest through them, with history's most interesting objects filed as bystanders. A brief accounting note for listeners keeping track of the clocks tonight. The figure of 10.7 billion years comes from the galaxy's redshift, measured at 2.18, meaning every wavelength of its light arrives stretched to more than 3 times its original length. Feed that stretch into the universe's measured expansion history, and out comes the travel time, and a curious consequence follows. The universe was expanding the entire time the light was in flight, so BX 442 is no longer 10.7 billion light-years away. Its present distance, whatever now means across such a gulf, is considerably greater, and its neighborhood, its descendant, and its fate have spent those 10 billion years receding from us at an accelerating pace. We will meet that arithmetic again in a few minutes, sharpened to its absolute limit at number 1. For now, it is enough to note that even our second-place mystery is an object whose portrait is ancient and whose address has moved, a subject that left the studio before the paint was dry. There remains one more turn, and it belongs to time rather than space, which is fitting so close to the top of this list. Everything we know about BX 442 describes a galaxy that has not existed, in that form, for 10.7 billion years. The light is a delivered letter from a sender long since transformed. In the eras since, that hot young disk has cooled or collided, grown or been consumed, and its transient spiral, if the models are right, dissolved within 100 million years of the portrait. Its descendant today is probably a massive, settled galaxy somewhere, perhaps a great elliptical that has not worn a spiral arm for billions of years, and we have no way to identify it, no way to check the ending, no way to see the galaxies now. This is the quiet vertigo of deep-field astronomy. Every image is an ancient history, every catalogue a list of the past. For BX 442, we possess a single frame of a film whose ending was decided before the Earth existed, and the projector cannot be run forward. And that vertigo, seeing only what was, never what is, brings us at last to the top of the list, to the most distant galaxy ever confirmed, an object whose light has traveled almost the entire age of the universe, and which sits, at this moment, permanently beyond the reach of anything we could ever send, including light itself. Number 1. Jade's GS Z140, the galaxy at the edge of forever. Number 1 on this list is the most distant galaxy ever confirmed, and it earns the top of a countdown about unreachable galaxies by redefining what unreachable means. Every entry tonight has been out of reach, the way the horizon is out of reach for a slow ship, a matter of impossible engineering, of lifespans too short and distances too long. The final galaxy is out of reach, the way yesterday is out of reach. No conceivable technology touches it. No signal, traveling at the fastest speed physics permits, launched at any moment from now until the end of time, will ever arrive there. The galaxy is called Jade's GZ140, and it holds two titles at once. It is the most distant object whose distance has been rigorously confirmed, and it is, in the strictest physical sense, the most permanently unreachable place humanity has ever identified by name. The instrument behind the record deserves its introduction, because this discovery is exactly what it was built to make. The James Webb Space Telescope, launched on Christmas Day of 2021, is a 6.5-meter mirror of 18 gold-plated beryllium hexagons, unfolded in space like a piece of ceremonial origami and stationed at the second Lagrange point, a gravitational balance spot 1 million miles from Earth on the planet's night side. It observes in infrared for a reason that this galaxy makes vivid. The expansion of the universe stretches ancient light out of the visible range entirely, so the deepest past arrives at Earth as heat, and a telescope that hunts the first galaxies must be a heat seeker, chilled behind its tennis court sunshield to within a few tens of degrees of absolute zero, so that its own warmth does not blind it. Hubble, magnificent as it was, simply could not see light this old. The distance record Hubble held for years, a galaxy called GNZ11 at redshift 10.6, marked the practical edge of its vision. Webb crossed that edge in its first months of science and kept going, and the manner of the crossing tells you how steep the new territory is. Within roughly 2 years of starting work, Webb had pushed the confirmed frontier from redshift 10.6 to 14.32, which in cosmic time means it moved our earliest confirmed galaxy about 400 million years closer to the beginning, deeper into the era its designers spent 3 decades promising it would open. Begin with the discovery, because it was a masterpiece of caution. When the James Webb Space Telescope began its deep surveys, one of its flagship programs was JADES, the J-Twist Advanced Deep Extragalactic Survey, a vast, patient photographing of 2 famous fields of sky, including a patch in the southern constellation Fornax that astronomy has been mining for decades. Webb's near-infrared camera, NEAR-CAM, imaged that field for hundreds of hours, stacking exposure upon exposure until galaxies from the universe's first few 100 million years rose out of the noise. Among the thousands of faint smudges, the survey's software and its astronomers flagged candidates whose colors suggested extreme distance. And color, here, means something precise. The early universe was filled with a fog of neutral hydrogen that devours ultraviolet light. A sufficiently distant galaxy, therefore, shows a sharp cliff in its spectrum, called the Lyman break, everything blueward of the cliff, erased by the fog. And as the universe's expansion stretches the galaxy's light, the cliff slides to longer and longer wavelengths. Find the cliff, and you have read the distance. But photometry, the reading of broad colors alone, can be fooled, and the field had already been burned. In Webb's first months, several celebrated candidate record breakers, deflated under closer inspection, revealed as nearer, dust-reddened galaxies wearing the costume of the early universe. The JADES team knew the stakes. So in January of 2024, they took the decisive step, pointing Webb's spectrograph, NIA-SPEC, at their best candidate for around 10 hours, spreading its feeble light into a true spectrum. The cliff appeared exactly where a record demanded, sharp and unambiguous, at a redshift of 14.32. The announcement came in May of 2024, and it has stood since. The record was real. The caution had a recent scar behind it, and the story is worth telling as science's self-correction working in public. In Webb's first summer, a candidate from another survey briefly captivated the field with colors suggesting a redshift near 16, which would have placed it impossibly early, and headlines duly appeared. When the spectrograph finally weighed in, the object collapsed to a redshift below 5, a dusty, star-forming galaxy at a thoroughly ordinary distance, whose particular mixture of emission lines had conspired, in the broad color filters, to counterfeit the Lyman cliff. The counterfeit taught everyone the price of enthusiasm, and it recalibrated the field's standard of proof overnight. That is why the JADES team's 10 hours of spectroscopy matter so much, and why the phrase "spectroscopically confirmed" is the dividing line running through every claim in this territory. Photometric candidates are letters of intent. Spectra are signatures. JADES GZ140 is signed, and among all the objects humanity has ever claimed at the edge of time, it is the deepest signature in the book. Now unpack what 14.32 means, because the number is doing extraordinary work. It means every wavelength of the galaxy's light arrives stretched to more than 15 times its original length, ultraviolet starlight delivered as infrared warmth. It means the light Webb collected traveled for roughly 13.5 billion years, almost the entire age of the universe. And it means we see the galaxy as it was about 290 million years after the Big Bang, when the universe was roughly 2% of its current age. If cosmic history were compressed into a single year, with the Big Bang at midnight on the 1st of January, this galaxy's portrait was taken in the second week of January, and the Sun will not form until early September. We are looking at the deepest photograph of the universe's infancy that carries a confirmed date. And the infant in the photograph is wrong. Delightfully, productively wrong. By every pre-Webb model of how galaxies assemble, an object at redshift 14 should be a barely there wisp, a faint knot of first-generation stars still gathering itself. JADES Z140 is a beacon. Its luminosity places it among the brightest galaxies known at any redshift beyond 8, so bright that, at first, the natural suspicion was a feeding black hole, a small quasar masquerading as starlight. Webb's imaging dismissed that escape route. The light is resolved, spread across a body some 1,600 light-years wide, which means it is the combined shine of a genuine stellar population. Hundreds of millions of solar masses of stars, already assembled, already blazing, within 300 million years of the beginning of time. Galaxies were not supposed to manage that. The finding is the sharpest specimen of what has become Webb's signature discovery, the surplus of bright, early galaxies, the young universe building luminous structure faster than our theories said it could. A galaxy is a place where gas becomes stars, we said at number 7, watching a galaxy that never began. Here is the same definition broken from the other side, a galaxy that finished too much, too fast, a place where gas became stars on a schedule no model had authorized. Between the galaxy that never started and the galaxy that could not wait, the rulebook of galaxy formation is bracketed by exceptions, and the honest lesson is that the universe applies its rules on its own schedule, not on the schedule our models proposed. A detail from the announcement is worth savoring. The record did not arrive alone. The same campaign confirmed a second galaxy in the same field, Jade's G's Z14-1, sitting just behind the record holder in redshift, a companion entry at the same impossible depth of time. Records at this frontier, it turns out, arrive in pairs and clusters, and that is itself informative. If bright galaxies at redshift 14 were freakish rarities, finding 2 in one small patch of sky would be wildly improbable. Finding 2 suggests the early universe made such objects in quantity that the deep fields are sampling a population, not stumbling on miracles. Every explanation now on the table has to produce them wholesale. Some theorists propose that early star formation was simply far more efficient, gas collapsing into stars with little waste in the dense conditions of the young universe. Others suggest the first stellar generations were top-heavy, minting an unusual fraction of massive, brilliant stars, so that a modest mass of stars shines with immodest light. Others note that the early universe may have held less obscuring dust, letting more of the light escape. None of these has won. All of them are being tested against Webb's accumulating census, and Jade's G's Z14-0 sits at the head of the table at every meeting, the specimen no model is allowed to fail. Then the chemistry arrived, and deepened the precocity into something stranger. Later in 2024, astronomers turned ALMA, the millimeter array in the Chilean Andes, toward the galaxy, hunting a specific whisper, the far-infrared radiation of doubly ionized oxygen, redshifted by the universe's expansion into ALMA's bands. They found it. A clean detection, confirming the distance independently and delivering a fact with real weight. There is oxygen in Jade's G's Z14-0. Oxygen does not come from the Big Bang, which manufactured essentially only hydrogen and helium. Every oxygen atom in existence was forged inside a massive star and released when that star died. Oxygen at redshift 14 means that by 290 million years after the beginning, this galaxy had already run complete stellar life cycles. Stars born, burned, and detonated, seeding the gas with their ashes, and only the most massive stars die fast enough to fit inside the window, giants living and exploding in mere millions of years. The detection is a census of a generation already dead when the portrait was taken. Astronomers describing the system reached for a telling word: mature. Follow-up observations added a complementary hint, searching for the radiation of ionized carbon that normally accompanies abundant cold gas and finding it absent, which suggests the galaxy's raw fuel is already partly processed or depleted. The most distant confirmed object in the universe does not behave like a beginning. It behaves like a place with history, an infant with a past, and nobody fully understands how the universe cleared room for history that early. Now come to the part that makes this galaxy the rightful summit of tonight's list, the arithmetic of never. 13.5 billion years of light travel does not mean the galaxy is 13.5 billion light-years away. All the while the light was in flight, the universe kept expanding, the road stretching behind and ahead of the traveler, and by the time the photons landed on Webb's mirror, their source had been carried to a present distance of roughly 33.8 billion light-years. And here is the fact on which this entire episode quietly pivots. The expansion of the universe is accelerating, and at that distance, the space between us and the galaxy is growing faster than light can cross it. Understand this carefully, because it is not a violation of physics. Nothing is moving through space faster than light. Space itself is stretching, and there is no speed limit on that. The galaxy is not fleeing. It is being carried, the way a boat at anchor is carried by a widening sea. But the consequence is absolute. The reachable universe, the volume from which a signal launched today could ever be answered or ever arrive, extends to a present distance of roughly 16 to 17 billion light-years. Beyond that line, the stretching wins, always and forever. Jade's G's Z14-0 stands at twice the line. A message transmitted tonight toward that galaxy, traveling at the full speed of light, without pause, without loss, will close the gap for eternity and never arrive, like a runner on a track that lengthens faster than she runs. At Malin 1, the beginning of tonight's list, we said the speed of light is not fast enough, and it sounded like a complaint about engineering. Here it is a law of nature. The speed of light is not fast enough. Nothing is. That is what the top of this countdown means by never. It helps, before the journey home, to lay the universe's three great circles side by side, because tonight's whole list has been climbing them. The first circle is the observable universe, everything whose light has had time to reach us, and its edge stands at a present distance of about 46.5 billion light-years, farther than the age of the universe times the speed of light, precisely because expansion has kept carrying the sources onward after their light departed. The second circle is the reachable universe, the 16 to 17 billion light-year sphere within which a signal sent today could still, someday, arrive. And the third circle is the neighborhood, the gravitationally bound, local group of galaxies, a few million light-years across, which is the only region that will remain with us permanently, because gravity has already won its local argument with expansion there. Notice the proportions. The volume we can ever touch is a small fraction of the volume we can see, and the volume we get to keep is a rounding error on both. Nearly everything astronomy studies, nearly everything on tonight's list, lives in the widening interval between visible and reachable, present to our instruments and absent to our futures, on display and out of stock. Jade's G's Z14-0 is simply the deepest catalogued resident of that interval, the object that makes the geometry impossible to wave away. And a note for the record books of the future. As of the making of this video, redshift 14.32 remains the confirmed frontier, with fainter, redder candidates queued behind it, awaiting spectra, and if one of them someday takes the crown, everything said tonight will simply transfer to a new address, slightly closer to the beginning. The record is provisional. The never is not. Ride the light home, once, to feel the whole span of it. You are a photon, ultraviolet and newborn, leaving a hot young star in Jade's GZ 14-0, 290 million years after the beginning of everything. You plunge outward through the fog of the infant universe, the neutral hydrogen thinning as the first generations of galaxies, your own among them, burn the mist away. Around you, over ages, the great structures assemble, threads and walls of galaxies knitting themselves across the dark, and the expansion stretches you as you fly, your wavelength lengthening, your color reddening, ultraviolet to gold, to deep red, to invisible warmth. Galaxies bloom and collide and settle along your route. 2/3 of the way through your journey, in an undistinguished spiral off to the side of your path, a yellow star kindles, and a system of worlds condenses around it, though you pass no closer to it than everything passes everything in this scattered universe. On the third world of that system, continents drift, seas rise, life complicates. In your final million years of flight, primates on that world stand upright. In your final few centuries, they build telescopes. And in the last instant of a journey 13.5 billion years long, you fall onto a hexagon of gold-plated beryllium, hanging at a quiet gravitational balance point, 1,000,000 miles from that third world, and you are absorbed and counted, and become a single faint pixel in an image reviewed by a species that did not exist for 98% of your flight. That is what a deep field is. Ancient light, caught at the last possible moment of its relevance, by observers who arrived almost too late for it. There is more to learn from the light we do receive, and the work continues. Deeper spectroscopy can inventory the galaxy's elements beyond oxygen, tracing exactly how enriched its gas had become, and thereby how many stellar generations preceded the portrait. Longer stares can sharpen its shape, hunting for structure inside those 1,600 light-years. A dense core, a hint of rotation, the first architecture of a disk. Each additional hour of telescope time develops the same single frame a little further, the way a photograph seems to yield new detail the longer you study it. But it is, and will always be, the same frame. Every future paper about Jade's GZ 14-0, every thesis, every revised model, will be an ever finer reading of one instant of one infancy, delivered once. Astronomy at this frontier is the scholarship of single photographs, and it has learned to be extraordinarily good at it, precisely because the universe offers no second sitting. And the catch is final, in a way that gives this galaxy its lasting melancholy. The light we hold is the only installment we will ever receive of its early story, and the story's continuation is sealed. The galaxy has spent the 13.5 billion years since the portrait, living a life we can reason about, but never witness. Presumably it grew, merged, flared, and settled, and its descendant today may be a giant elliptical indistinguishable from 1,000,000 others, perhaps the anchor of its own cluster, perhaps long since consumed by something larger. We will never know. Its present is not late-breaking news that has yet to arrive. It is news that can never arrive, carried by light that loses the race against the stretching road. And every year the race grows less winnable, as acceleration carries the galaxy further beyond the line. Astronomers sometimes note, as a quiet aside, that cosmic acceleration is slowly emptying our future sky, carrying galaxy after galaxy across the unreachability line, tens of thousands of them receding beyond reply in a human lifetime. The universe's reachable inventory only ever shrinks. There is even a gentle deadline written into the record itself. In the deep future, tens of billions of years on, the ongoing stretch of space will have shifted this galaxy's light beyond any practical detection, its already faint infrared whisper lengthened toward wavelengths no instrument collects against the sky's own noise. Astronomers of that era, whoever and whatever they are, will inherit a sky in which the deep past has faded from view, and they may never be able to establish, by observation, what we established in May of 2024. Knowledge of the early universe, it turns out, has a season. We happen to live in it. We hold one baby picture of the most distant thing we have ever confirmed, an infant that broke the rules in the first frame, and the universe has arranged its geometry so that the rest of the album is not lost, not hidden, but structurally undeliverable. No future civilization, however patient, however advanced, gets that album back. Reach and understanding, it turns out, are two different things, and only one of them has a limit. So the countdown completes, and the inventory we opened 3 hours ago can be closed and put away. A galaxy shines, we said, and Malin 1 and J0613 plus 52 decline. A galaxy trails its arms behind its spin, and NGC 4622 leads with them. A galaxy holds its dark matter, and DF2 stands foundationless, while Dragonfly 44 is little else. A galaxy keeps its black hole, and the giant of Abel 2261 keeps an empty room. A galaxy takes its time, and BX 442 and Jade's GZ140 arrived early, finished and shining before the universe was ready for them. 10 galaxies, 10 crossings out, and not one of them within reach, ever, of anything we build or become. Perhaps that is the right condition for wonder. The sky keeps its finished answers at distances where our only instruments are patience and light, and it lets us understand, generously, everything except the endings. Let the 10 of them turn where they are, the invisible giant, the perfect ring, the backward wheel, the unlit disk, the burning engine, the 2 ledgers, the empty throne, the early architecture, and the infant at the edge of forever, each carrying its unsolved question through the dark at its own unhurried pace. They will still be turning and still unreachable when this night and every night like it is over. Sleep well and good night.